Welcome back to Sleep Nova. Sit back, relax, and don't forget to comment where you're watching from down below. It's amazing seeing people all around the world supporting my small channel. Now, enjoy the show. Cosmos. The word itself is like a soft whisper in the dark of night, inviting us to look up and wonder. Born from ancient Greek, it means order or ornament, the opposite of chaos, the adornment of the night sky. For as long as humans have had language, we have given a name to the grand scheme of everything. We have always stood under the starry vault, hearts beating with curiosity, minds aching to understand what it all means. In a silent desert or on a grassy hill, our ancestors gazed at the stars with awe. Tiny lights flickering in the vast darkness became stories, became gods and guides. Under that cosmic canopy, they felt small, yet connected to something immense. They sensed in those pinpoints of light a pattern, a rhythm, seasons changing, moons waxing and waning, a cosmos moving with purpose. To say cosmos is to imply the universe is not a random scattering of matter, but a harmonious whole. Beyond the chaos of daily life lies a greater order we can barely fathom. When we whisper the word, we summon an ancient feeling, the awe of knowing we are part of a mysterious, breathing entirety. The cosmos has always beckoned us. It humbles us with its scale and age, yet it also comforts us with the idea that we belong to it. We have wondered if the twinkling lights had messages for us, if the sky was a story written in stars. Generation after generation, we pass down myths and measurements, trying to bring the heavens into human understanding. Through wonder and imagination, we wove ourselves into the fabric of the cosmos. Even now, in an age of bright cities and glowing screens, that old impulse remains. Go somewhere dark and clear, and look up. The same Milky Way that dazed our ancestors arches overhead. In that band of light, millions of distant suns blurred together, we find both our history and our destiny. We feel the tug of an ancient question with each breath under the stars. What is all this? What does it mean that we live in a cosmos so vast and beautiful? From the earliest times, cosmos has meant more than just the physical universe. It carries a sense of profound order and connection. To reflect on the cosmos is to step beyond oneself, to see life on Earth as part of a larger story. It is to realize that the atoms in our bodies were born in stars, that our existence is tied to cosmic events beyond memory. It is to feel both tiny and tremendous, a fleeting moment and an integral part of eternity. So let us meditate on that word and all it entails. Let us journey outward and backward, upward and inward. In this story of the cosmos, we will travel from ancient myths to modern science. We will seek patterns in the sky that guided our ancestors and follow the light of distant galaxies that reveal our cosmic origins. We will ponder forces unseen and marvel at galaxies strung like jewels on invisible threads. Through it all, we hold on to that childlike wonder that first taught us to say cosmos with reverence. Our voyage begins where it must, in the tales and dreams of those who first looked up and tried to understand. The cosmos has always been our mirror and our muse. In its vastness, we have found grand myths of creation, of gods and monsters, of order emerging from chaos. To truly know the cosmos, we start with the ancient stories written not on paper, but across the sky itself. The ancient cosmos. Before science, there were stories. In the cradle of civilization, human beings looked to the sky and saw a grand drama unfolding above. The cycle of night and day, the march of seasons, the wandering of planets among the stars. All these celestial motions cried out for explanation. And so our ancestors gave the cosmos a face, a script, a meaning. The ancient heavens became a mirror of life on Earth, a canvas on which they painted their hopes and fears. In ancient Egypt, each sunrise was not just a new day, but a victory of order over darkness. The sun was the god Ra, sailing across the sky in his brilliant boat. Every morning he was reborn in the east, bringing light and life. Every evening he descended into the underworld, battling forces of chaos to ensure the sun would rise again. To the Egyptians, the cosmos was upheld by these divine cycles. Ra's daily journey affirmed the rhythm of life, death, and renewal. The Nile would flood and recede, crops would grow and be harvested, just as surely as the sun would set and rise. Their myths gave cosmic meaning to earthly patterns, reassuring them that the universe was orderly and life-sustaining as long as the gods maintained balance. Far to the north, under Greek skies, people also sought cosmic order through myth. They imagined the night as a storybook opened overhead. Constellations were characters, a great hunter forever chasing a bull across the heavens, a hero carrying the weight of the sky on his shoulders, a queen enthroned among the stars. The Greeks looked up and saw legends. Orion with his shining belt of 3 stars, majestic and bold, the Great Bear lumbering around the North Pole, Andromeda chained to her stellar rock. Each constellation marked a tale of love or bravery or caution, a lesson twinkling from the firmament. Above all reigned Zeus, king of the gods, whose authority extended over both the sky and human affairs. The moving planets, the wanderers, were given names and personalities: fiery Ares, Mars; bright Aphrodite, Venus. By telling these tales, the Greeks found patterns in the stars, a cosmic order reflecting their own virtues and vices. The movement of the heavens hinted at divine plans. If Mars appeared red and bright, was Ares signaling war? If Venus rose in the evening, did Aphrodite bless lovers? In this ancient cosmos, the boundary between heaven and earth was thin, each influencing the other. Across the ocean in other lands, countless cultures wove their own cosmic tapestries. In old China, the night sky was envisioned as a celestial empire mirroring the earthly one. The emperor was said to be the son of heaven, and the stars were arranged into palaces and provinces. The Chinese sky was divided into constellations, forming a meticulous heavenly bureaucracy. A comet streaking through the sky might be interpreted as a wayward official or a portent of change in the kingdom. An eclipse was not just an astronomical event, but a dragon devouring the sun or moon, a sign that the harmony of the cosmos had been disrupted. To restore balance, people gathered to beat drums and gongs, scaring the dragon away. When the sun returned, it reaffirmed the cosmic order and the emperor's mandate. Through such rituals and myths, the ancient Chinese made sense of celestial motions as reflections of moral and political order on Earth. In the Indian subcontinent, sages imagined a layered cosmos teeming with gods and avatars. The sky was the abode of deities riding the clouds. The sun was Surya, a radiant god who drove his chariot across the heavens, pulled by 7 horses, the colors of sunlight. The moon was Chandra, gentle and cool, gliding through the night. The planets were also gods, each with personality and power, collectively called the Navagraha. Indian cosmology spoke of a universe born from a cosmic egg, of endless cycles of creation and dissolution measured in kalpas, lasting billions of years, staggering spans of time encoded in myth. Yet these huge cycles tied into everyday life. The positions of planets could influence a person's destiny, the timing of rituals, the fortunes of kings. By observing the heavens, ancient Indians felt they could glimpse the divine rhythm that underpins reality, aligning their lives to the dance of the cosmos. No matter where on Earth, early peoples found ways to map the sky onto their own experience. The Babylonians meticulously tracked the movements of planets and stars and wove them into their myths of gods like Ishtar, Venus, and Marduk, Jupiter. They recorded eclipses and believed in cosmic omens, that a falling star could foretell the fall of a king. The Maya of Central America built observatories to follow the sun and Venus, timing agriculture, and ceremonies to celestial cycles. For them, the cosmos was a ceaseless wheel of time, with each era ruled by different gods. Indigenous peoples of North America saw constellations as great hunters and animals, integrating the sky into storytelling and navigation. Every culture found its own cosmic North Star by which to guide human life. These ancient cosmologies differed in detail, but they shared a purpose: to make the vast, unknowable sky intimate and meaningful. By projecting stories onto the stars, our ancestors found comfort and guidance. The cosmos became a grand clock and calendar, its motions providing a sense of predictability in an uncertain world. The rising of Sirius just before dawn signaled the Nile's flood, and thus renewal, to the Egyptians. The appearance of the Pleiades in spring told Greek sailors that sailing season had arrived. The heavens and earth were interwoven in a tapestry of sign and story. Most importantly, the ancient myths gave people a sense of belonging in a huge universe. If the heavens were populated by gods and heroes, then human life was part of that divine drama. Nothing was random. The cosmos had intention, personality, narrative. A shooting star could be a departing soul. The Milky Way could be the spilled milk of a goddess or the bridge to the afterlife. By aligning with these cosmic stories, performing rituals at solstices, building temples to face sunrise, tracing the planet's paths, ancient humans felt they were participants in the cosmos, not mere spectators. In those early nights under open skies, the cosmos was both guide and canvas. People drew connections between the circling stars and the cycles of their own lives. Birth, death, love, conflict, harvest and drought, all found reflection in the movements above. The myths may not have been scientifically accurate, but they were true in a deeper sense. They captured the emotional truth of being human in a vast and mysterious universe. They helped us navigate not just by land or sea, but through the uncharted waters of existence. Thus, the ancient cosmos was a place of narrative and meaning. It was alive with motion and intention. Every sunrise was a story, every eclipse a warning or wonder, every constellation a reminder that we are part of something greater. With these stories, humanity's long conversation with the stars began. Over millennia, those conversations led to patterns noted, calculations made, and the first whispers of a new approach to understanding the cosmos. Myth would eventually inspire measurement, and storytelling would lead to science. As our methods changed, the goal remained the same: to find our place in the grand order of the cosmos, and to ensure that the cosmos made sense. The birth of the modern cosmos. For thousands of years, the Earth sat proudly at the center of the known universe in human imagination. It seemed obvious. The ground beneath us felt still and solid, while the heavens whirled around. The sun rose in the east, journeyed overhead, and set in the west, surely circling us. The stars rotated nightly around the North Star, as if painted on the inside of a celestial dome with Earth at its core. This geocentric cosmos, codified by philosophers like Aristotle and Ptolemy, was cozy and reassuring. Humanity lived at the heart of creation, the focal point of God's plan or nature's design. Above, the crystal spheres turned in orderly concentric circles, carrying the sun, moon, planets, and stars in divine choreography. In this model, the cosmos was finite, well-ordered, and centered on us. But whispers of a different truth had long existed. As early as ancient Greece, a few bold thinkers, like Aristarchus, suggested that the Earth might move around the sun. This idea was largely dismissed or forgotten for centuries. It simply felt wrong. How could Earth be moving? We felt no incessant wind from such motion, no constant shaking. And if Earth swung around the sun, where was the parallax in the stars? The tiny shift in star positions that such motion should produce? None could be seen with the naked eye. so the geocentric view held sway through antiquity and the Middle Ages. Then, in the 16th century, a Polish astronomer named Nicholas Copernicus quietly revolutionized our view of the cosmos. He proposed a bold simplification. Suppose the Sun is at the center, and the Earth is just another planet circling it. In one stroke, the cosmic order could be explained more elegantly. The retrograde loops of Mars in the sky, the cycles of Venus, all made sense if Earth was moving too. Copernicus published his heliocentric theory in 1543, carefully dedicating it to the Pope and couching it as a mathematical convenience. Yet the implication was clear. Our planet was not the pivot of creation. It was a radical leap, met with skepticism or silence by most contemporaries. After all, it upended common sense and challenged religious doctrine. But the seed of the modern cosmos was planted. It would take brave observers and thinkers to make that seed sprout. Early in the 17th century, Galileo Galilei in Italy heard of a new invention, the telescope. He crafted his own and pointed it at the night sky, becoming the first human to see certain wonders. Through Galileo's telescope, the moon revealed mountains and craters, not the perfect heavenly orb philosophers imagined. Jupiter appeared as a tiny disk, accompanied by 4 points of light that moved, Jupiter's moons, orbiting not Earth but Jupiter itself. It was a celestial ballet defying geocentric dogma. Here were objects clearly circling a world other than our own. Galileo also observed Venus showing phases like the moon, a behavior only possible if Venus circled the Sun, not Earth. Star clusters and the Milky Way resolved into countless faint stars, suggesting the cosmos was far larger and richer than assumed. With each observation, Galileo dealt blow after blow to the Earth-centered model. He wrote of his findings, championing the Copernican sun-centered system. This earned him admiration among some and condemnation from others. The idea that Earth moved was still too great a heresy for many. Galileo famously faced the Roman Inquisition and was forced to recant. But the truth was out. Our world was not the fixed center. Earth was a planet in the heavens, one among several. With the heliocentric model gaining evidence, the cosmic stage expanded. Johannes Kepler refined the picture by discovering that planets travel in ellipses, not perfect circles, and speed up and slow down in their orbits according to precise laws. It was as if the cosmos had its own music, and Kepler had begun to hear its rhythm in the data. Shortly after, Isaac Newton in England provided the masterstroke. He formulated the law of universal gravitation, showing that the same force pulling an apple to the ground keeps the moon circling Earth and Earth circling the Sun. In Newton's new universe, the celestial and terrestrial were unified. The heavens were not held up by crystal spheres or angelic powers, but by gravity, an invisible thread binding planets to stars. Suddenly, the cosmos became a mechanistic marvel, a grand clockwork governed by laws that could be understood and even predicted by humans. The music of the spheres was transcribed into mathematics. The modern scientific cosmos was being born, and in it, Earth was merely one cog in a vast machine. As the centuries turned, our understanding leapt forward. By the 19th century, astronomers realized the Sun itself was not the center of all creation, but rather the center of a local family of planets. The stars, once thought to be distant lanterns or holes in the firmament, were confirmed to be other suns scattered across unimaginable distances. The night sky, which to the ancients was a fixed dome, became an ocean of stars in 3 dimensions. We measured the first distances to stars and found them stupefyingly far. The nearest, Alpha Centauri, is over 4 light-years away, 40 trillion kilometers. The absence of observed parallax now made sense. The stars were vastly farther than imagined in Aristotle's time, so their parallax was tiny. Our Sun was thus not the center of all stars, but just one star drifting in a great starry city. That starry city is the Milky Way galaxy, a broad band of light wrapping the sky. In the early 20th century, astronomers pieced together that the Milky Way was an immense disk of hundreds of billions of stars. Our sun lay not at the center of this disk, but off to the side in a spiral arm, a suburban star in the galaxy's outskirts. We had been demoted once again from center of the universe to mere resident of one galaxy among possibly many. Yet even then, many believed the Milky Way was the entirety of the universe, an island universe surrounded by a void. Reality had another plot twist in store. In 1920, astronomers Shapley and Curtis engaged in the great debate over the scale of the universe, arguing whether spiral nebulae, like Andromeda, were part of the Milky Way or distant galaxies of their own. This question was settled in the mid-1920s when Edwin Hubble, using the giant Mount Wilson telescope, observed stars in the Andromeda Nebula. He identified particular stars called Cepheid variables, whose blinking rhythm allowed him to calculate their distance. The result was staggering. Andromeda was far outside our Milky Way, a galaxy in its own right. In one announcement, Hubble shattered the confines of our known cosmos. The universe was vastly larger than we had imagined. The Milky Way was but one galaxy among billions spread throughout space. As if that weren't enough, Hubble soon discovered that these galaxies are flying apart from each other. Space itself is stretching. The spectra of distant galaxies were shifted toward the red, like the lowered pitch of a receding siren, indicating they were rushing away. The farther the galaxy, the faster it fled. It was as though the cosmic fabric were inflating, carrying galaxies apart like driftwood on a rising tide. The implication was profound. If you rewind this expansion, there was a time when everything was closer together, perhaps a moment when the entire universe was a single point. The static, eternal cosmos of old gave way to a cosmos with a dynamic history, a beginning, what we now call the Big Bang, and perhaps an end. Thus, in just a few centuries, our cosmic understanding transformed utterly. We went from a cozy Earth-centered bowl of stars to an immense, law-governed expanse where Earth is a moving planet, the Sun a modest star, the Milky Way one galaxy among a multitude, and the universe itself expanding and evolving. Each step was a blow to human vanity, but a boon to human knowledge. With each step, the cosmos grew grander and more mysterious, yet also more knowable through science. The modern cosmos was not built in a day. It emerged gradually as old theories shattered and new discoveries took their place. It required curiosity, courage, and the willingness to accept that our intuitions can be wrong, that reality may be far stranger and more magnificent than our ancestors ever dreamed. By embracing a sun-centered system, by mapping the Milky Way, by discovering galaxies beyond our own, humanity experienced a kind of cosmic rebirth. We shed ancient illusions and stepped into a wider universe, guided by observation and reason. And as the scale of the cosmos expanded, so did our sense of wonder. The night sky, once a fixed storybook of constellations, became an endless frontier. We now knew that when we gaze at the Milky Way, we peer into the heart of our galaxy, and when we spot the faint smudge of Andromeda, we behold a sister galaxy 2.5 million light-years away. The light entering our eyes left that galaxy before our species existed. The modern cosmos is vast, full of galaxies drifting in the darkness, all governed by the same natural laws. This was a cosmos that could be analyzed with telescopes and equations, but it still evoked awe. In fact, the more we discovered, the more profound and humbling the mystery became. Having found our true place, not the center, but part of a cosmic community of worlds, we were ready to explore what this newfound universe looked like. With minds freed from the confines of geocentrism, and with ever more powerful tools, we set out to observe the cosmos in all its glory. The next step of our journey would be to truly behold the universe with new eyes. to collect the ancient light of stars and galaxies, and from it, read the story of time itself. The Observable Cosmos. Armed with newfound knowledge and powerful eyes, humanity set out to truly see the cosmos. What had been mysterious points of light became tangible suns and galaxies through the lens of the telescope. Our curiosity, once limited by human sight, now leapt forward with each improvement in our instruments. The cosmos opened like a book under a magnifying glass, revealing detail upon detail written in light. We learned a startling fact. To observe the universe is to look back in time, for light takes time to travel. Consider the starlight reaching us tonight. The nearest star beyond our Sun, Proxima Centauri, lies 4.24 light-years away. The light hitting our eyes from that star left it over 4 years ago, crossing trillions of kilometers of space before gently landing on our retina. We see Proxima Centauri not as it is now, but as it was 4 years in the past. And that's our nearest neighbor. Sirius, the brightest nighttime star, shines 8.6 light-years away. We see it as it was about when the last decade began. The North Star, Polaris, is 433 light-years distant, so the light guiding sailors tonight set off around the time Galileo first pointed a telescope skyward. With every step up in distance, we peer further back in time. The Andromeda Galaxy, faintly visible as a smudge, is over 2 million light-years away. When its light began its journey, early hominins on Earth were chipping stone tools. This realization transformed the night sky into a kind of cosmic history book. Telescopes became our time machines, collecting ancient photons that have been traveling for eons. By capturing this light and studying it, we decode stories from long ago and far away. The color and brightness of a star's light tells us its composition and temperature. The Doppler shift of a galaxy's light reveals its motion through space. When we see the glittering band of the Milky Way, we now understand it as the combined glow of billions of stars, many whose light has traveled tens of thousands of years to reach us. To look out is to look back. As telescopes grew in size and sophistication, the depths of the observable cosmos unfolded. In the 19th century, astronomers with new refractors and reflectors saw that some fuzzy patches of light, nebulae, had spiral shapes. They suspected these might be island universes, galaxies outside our own, later confirmed by Hubble. Each advance in observational power was like opening a new window in our cosmic house, offering a view further into space, and thus further into the past. In the 20th century, we launched telescopes above the blurring veil of Earth's atmosphere. The Hubble Space Telescope, deployed in 1990, proved transformative. Free from atmospheric distortion, Hubble could stare deeper into space than any instrument before. In 1995, astronomers did a daring experiment. They pointed Hubble at a seemingly empty, dark patch of sky near the Big Dipper, where no known stars or galaxies were visible, a speck of sky no bigger than a grain of sand held at arm's length. They let Hubble's camera soak in light for 10 straight days. What came back was a revelation: the now famous Hubble Deep Field image. Far from empty, that little patch of darkness was overflowing with nearly 3,000 galaxies, of all shapes, sizes and colors, each a swarm of billions of stars. Some were relatively nearby, but many were incredibly distant, their light having traveled for billions of years. In those dim smudges, Hubble had captured galaxies as they were when the universe was young, cosmic baby pictures, just a few billion years after the Big Bang. That single image was like a core sample of the universe, drilling down through cosmic time. It showed a universe teeming with galaxies, even in a tiny, unremarkable bit of sky. Later, Hubble gazed even longer and deeper, producing the ultra-deep field in 2004, and then the extreme deep field in 2012, revealing galaxies more than 13 billion years in the past, when the first galaxies were just emerging. In the Hubble ultra-deep field, Almost every point of light is an entire galaxy. Some are seen as they were only 400–800 million years after the Big Bang, full of newborn stars. By looking far away, we looked back to a time when the universe was young. Every telescope, whether a backyard amateur's or a great observatory in space, is fundamentally a light collector. It gathers the sparse, ancient photons that rain down on us, focusing them into an image or feeding them to instruments that can analyze their secrets. Through visible light telescopes, we see stars and galaxies as our eyes would, only fainter and farther. Through radio telescopes, we tune in to the whisper of the cosmos at long wavelengths, the songs of cold hydrogen clouds and the ghostly crackle of remnant radiation from the Big Bang. Infrared telescopes peer through cosmic dust to find stars being born in swaddling nebulae and detect the faint glow of the most distant galaxies whose light has been stretched to infrared by the expanding universe. Ultraviolet and X-ray telescopes capture high-energy phenomena, flares on stars, the glow of gas around black holes, the hot plasma in galaxy clusters. Each portion of the electromagnetic spectrum is like a different chapter of the cosmic story, and we've learned to read them all. The observable cosmos extends far beyond what human eyes alone can see, thanks to these extensions of our senses. Perhaps the most ancient light of all that we have observed is the cosmic microwave background, the cooled, faint afterglow of the Big Bang itself. Discovered by accident in 1965 as a pervasive microwave hiss in a radio antenna, this all-sky glow is the light from about 380,000 years after the Big Bang, when the hot plasma of the early universe finally cooled enough to become transparent and release photons in all directions. We see it now as a uniform microwave glow coming from every direction, just a few degrees above absolute zero, the oldest fossil of light, nearly 13.8 billion years old. Detailed maps of the microwave background made by satellites, COBE, WMAP, Planck, show it's mostly uniform but with tiny variations in temperature, the seeds of all future cosmic structure. This is literally a baby picture of the universe, long before stars or galaxies existed. It's a reminder that our telescopes have pushed our vision to its limit. We can nearly see the Big Bang itself. Within the observable cosmos, we have catalogued wonders beyond count. We've seen star clusters with hundreds of thousands of suns, nebulae that are stellar nurseries sculpted by winds and radiation, galaxies colliding and merging in dances that last hundreds of millions of years. We have detected planets around other stars by the subtle dimming of starlight or the wobble of spectral lines. We now know planets are common, numbering in the billions in our galaxy alone, from hot Jupiters skimming their stars to Earth-like rocks in temperate orbits. We've measured the universe's expansion and even glimpsed its acceleration due to an enigmatic, dark energy. All of these achievements flow from extending our senses with instruments and collecting the light, or other radiation, that streams through space, carrying messages from afar. Telescopes, in a poetic sense, gave the universe a voice in time. Through them, we listen to the echoes of the past. When we look at a distant galaxy cluster, we might be seeing it as it was when our own sun had not yet formed. In the faint glow of a red-shifted galaxy, we might be witnessing an event that occurred shortly after the dawn of time. The observable cosmos is a time capsule cosmos. The phrase observable universe also reminds us of limits. Light from extremely distant regions hasn't had time to reach us in the 13.8 billion years since the Big Bang, so there are horizons we cannot see beyond, at least not yet and maybe not ever, if the expansion accelerates. This doesn't mean those regions don't exist, just that they lie beyond our view. So the observable cosmos, everything we can see or detect, is still potentially only a piece of a larger whole. But it is grand enough, about 93 billion light-years across today, accounting for expansion, containing perhaps 2 trillion galaxies. Each of those galaxies, in turn, contains billions or trillions of stars, and around many of those stars orbit worlds we are only beginning to discover. Looking up from Earth, a small creature on a small planet, we now can perceive structures and events on scales our ancestors never imagined. We have essentially pulled back the curtain of distance, and what we found is a universe that is dynamic and changing. The sky is no longer a fixed backdrop, it is a living history. Every point of light is a story unfolding. Some star being born in a nebula, another nearing its death as a red giant, a galaxy swirling in a gravitational dance with a neighbor, a supernova shining briefly like a cosmic firework. We catch these events mid-stride, like reading random pages from a vast novel. Telescopes allowed us to no longer be passive inhabitants of the cosmos, but active witnesses to its grand story. Each night an observatory opens its dome and points its giant eye outward. We extend our reach farther in space and further back in time. We do this not for conquest, but for understanding, to fill in the chapters of the cosmic story from the beginning until now. And through these observations, we have come to see the universe not as static, but as an unfolding tale with a beginning, middle, and ongoing narrative. Having surveyed what we can see, the stars and galaxies and background glow, we noticed a grand pattern in how matter is arranged on the largest scales. Galaxies are not scattered randomly. They form a vast cosmic web of filaments and voids. To this we now turn, the large-scale structure of the universe, the cosmic web that gravity built, seeded by tiny quantum ripples from the dawn of time. The cosmic web. On the grandest scales, the universe is organized into a vast cosmic web, a structure both simple and intricate, like lace stretching across unimaginable distances. If we could zoom way, way out beyond our galaxy, clusters of galaxies would begin to outline a pattern. Galaxies are not evenly sprinkled through space, but collected in filaments, sheets, and dense knots, clusters, with huge voids between them where few galaxies reside. The cosmos, viewed from afar, resembles a web or sponge, bright threads and nodes of matter surrounding dark, empty bubbles. Gravity is the master architect of this cosmic web. Over billions of years, gravity drew matter together, amplifying tiny primordial irregularities into the vast structures we see now. In the early universe, matter was nearly uniform, with slight denser spots here and there, imprinted as those tiny temperature ripples in the cosmic microwave background. As the universe expanded and cooled, these denser spots, seeded by quantum fluctuations and stretched by inflation, exerted a bit more gravitational pull, drawing in surrounding gas and dark matter. Over time, the slightly denser regions grew into filaments and clumps. The empty regions gave up matter to the crowded ones and became enormous voids. Imagine flying through a slice of the universe a few billion light-years across. For millions of light-years, you might see almost nothing, traversing a void where only the occasional dim galaxy or wisp of hydrogen appears. Then, ahead, you'd see a filamental chain of galaxies stretching across space like a gossamer strand. Drawing closer, that filament resolves. It's a chain of galaxy clusters connected by thinner tendrils of galaxies. You follow the filament to a nexus, a rich cluster of galaxies where filaments intersect, perhaps like the Coma cluster containing thousands of galaxies swarming around a common center. From that hub, multiple filaments radiate out, each leading to other clusters. This is the cosmic web, clusters, nodes, connected by filaments, separated by voids. It's akin to the structure of a sponge or foam, an interlocking network of walls and channels. Our own Milky Way lies within this web. It is part of a small cluster, the local group, which in turn is on the outskirts of a larger Virgo cluster. That cluster is part of a filament that stretches toward the Great Coma cluster. In fact, astronomers have mapped our local section of the cosmic web and found that our local group, Virgo cluster, and other nearby clusters are all part of a supercluster system they've named Laniakea, Hawaiian for immeasurable heaven. Gravity is drawing our local group, including the Milky Way and Andromeda, toward the Virgo cluster, and all of Virgo and its neighbors toward an even larger concentration called the Great Attractor. Our galaxy, in the far future, will drift along the web into those larger structures, though perhaps not before dark energy's expansion halts that motion, an evolving contest between expansion and gravity. One of the striking things about the cosmic web is how empty the voids are. Some voids span hundreds of millions of light years with almost no galaxies. In contrast, the filaments and clusters are crowded. In massive clusters, galaxies can be just tens of thousands of light years apart, very close in cosmic terms, and space between them is filled with hot, X-ray emitting gas, heated by the gravity of the cluster. The filaments themselves contain not just the galaxies we see, but also lots of dark matter and diffuse gas connecting cluster to cluster. In fact, simulations and observations suggest that most of the ordinary matter, atoms in the universe, resides not in galaxies, but in the filamentary tendrils of warm, hot intergalactic medium, WIM, threading the voids. It's like an invisible scaffold. The galaxies are like dewdrops on a spider web, outlining it, but much of the web itself is faint and hard to see directly, composed of thin gas and especially dark matter. Dark matter, that mysterious substance making up about 85% of the matter in the universe, is the backbone of the cosmic web. While ordinary gas can radiate energy and settle, dark matter does not radiate, so it forms large, diffuse halos. It was dark matter that first clumped due to gravity, with ordinary matter later falling into the gravitational wells the dark matter created. In supercomputer simulations of cosmic structure formation, one starts with a nearly uniform distribution of dark matter, with tiny random density fluctuations, and lets gravity work over billions of years. The result is a filamentary network, extremely similar to what large galaxy surveys observe. The bright nodes in such simulations correspond to where clusters of dark matter, and later galaxies, form. The long dark strands correspond to filaments of dark matter along which galaxies and clusters align. The empty regions correspond to voids evacuated of matter. It's a beautiful example of emergent order. Out of near uniformity emerges complexity, a cosmic web, simply from the action of gravity over time. Tiny fluctuations in density, originating from quantum jitters in the infant universe, became the template for everything. Stars, galaxies, clusters, the web. The cosmic web is the largest pattern we know. It shows that on the grandest scales, the universe has a structure, homogeneous and isotropic, only when averaged over truly enormous volumes, but locally clumpy in a sponge-like way. It's often said that the universe on very large scales looks the same everywhere, the cosmological principle. And it's true that if you average over hundreds of millions of light years, one region is much like another in terms of galaxy counts. But zoom in a little less and the web stands out. Homogeneous only in a statistical sense, but in reality threaded and bubbled. It's intriguing to note parallels between the cosmic web and other networks. The distribution of matter in the universe, as revealed by galaxy surveys like the Sloan Digital Sky Survey, bears a resemblance to the neural networks in brains, or the large-scale structure of the internet. Hubs and spokes, clustering of connections. This might just be a coincidence of pattern. Nature finds similar solutions to connectivity problems, or possibly a hint of deep universal principles of self-organization. When scientists compared the network properties of the cosmic web and the network of neurons in a brain, they found tantalizingly similar complexity and distribution despite the difference in scale by 27 orders of magnitude. It's a reminder that simple laws, like gravity's inverse square attraction and expansion of space, can create intricate structures mirrored elsewhere in nature. Crucially, the cosmic web is not static. It's still evolving. Over time, gravity will continue pulling matter along filaments into clusters. The rich get richer, clusters accumulate mass, and the voids get emptier. Superclusters may merge into even larger structures, sometimes called hyperclusters, though there's a limit. Eventually, dark energy's accelerated expansion will push galaxies away from each other faster than gravity can overcome. It's thought that in the far future, 100 billion years or more, distant clusters will recede beyond our observable horizon, effectively isolating each remaining cluster or group as its own island universe. At that point, any cosmic web structure beyond our local cluster will be unobservable. The larger pattern will be lost to view, though it will still exist beyond our reach. For now, however, we live at a time where we can map the cosmic web, see its glory, and use it to test our theories of cosmology. Understanding the cosmic web helps answer profound questions. How did the universe transition from the near-uniform fireball after the Big Bang to the rich hierarchy of structure we see now? The answer: the interplay of gravity, pulling matter into structure, and expansion, spreading things out, created a foam-like arrangement. Tiny fluctuations grew to filaments, matter flowed like rivers into cluster basins, and vast quiet voids were left where nothing much happens. Having journeyed from our planet to the galaxy, to clusters and the cosmic web, we've framed the large-scale architecture of the cosmos. But what holds this architecture together? And what threads run through every level of this tapestry? For that, we must discuss the fundamental forces and fields: gravity, electromagnetism, and the nuclear forces, the hidden framework, underlying movement and structure everywhere in the cosmos. Forces and fields. In the grand ballet of the cosmos, 4 fundamental forces choreograph every move. They are the unseen influences that shape everything from the orbits of planets to the light in our lamps to the fusion in stars. Though invisible, they form a hidden framework that makes the universe dance. Each force is like a different instrument in an orchestra, and together they compose the music of the cosmos, from the smallest scales to the largest. Gravity is the most familiar, and yet in many ways, the most mysterious. It is the sculptor of the cosmos, the gentle but persistent pull that guided matter into spheres and orbits. Every time an apple falls from a tree, or we feel our own weight, we are feeling gravity. This same force reaches across the emptiness of space to keep the moon circling Earth and Earth circling the sun. It binds solar systems and steers stars around the centers of galaxies. It gathered galaxies into clusters along the cosmic web. Gravity is by far the weakest of the 4 forces on small scales. A tiny magnet can lift a paperclip against the entire Earth's gravity. But over large scales it dominates because it only attracts and never cancels out. Over time, its tiny tug accumulates into an inexorable current that builds structure. Einstein revealed that gravity is not a force in the traditional sense, but a curvature of space-time itself. Mass and energy bend the fabric of space and time, and objects move along those curves. The sun dents space-time, and Earth rolls around that dent like a marble in a bowl. This elegant understanding tells us gravity is the shape of the cosmos's geometry. It's what gives the universe its large-scale structure, what makes a cloud of gas collapse into a star, what pins us to our beloved Earth. Gravity is both patient and powerful. Given enough time, it can gather raw matter into galaxies or crush a star into a black hole. Largely, though, gravity is the quiet, persistent heartbeat of the cosmos, keeping worlds in their courses and the celestial architecture intact. Electromagnetism is the artist and communicator of the universe. It is the force responsible for light itself. Every beam of starlight traveling to our eyes is an electromagnetic wave. It also binds atoms and molecules. It's the reason you do not fall through the floor. The electrons in your shoes repel the electrons in the floor. Electromagnetism is vastly stronger than gravity at small scales. It's what makes magnets cling and lightning crackle, what lets compasses point north and radio waves carry music. In atoms, the electromagnetic force binds negatively charged electrons to positively charged nuclei, forming atoms. It causes atoms to link into molecules by sharing electrons, giving us the variety of chemistry. The warmth you feel from sunlight, the colors of a rainbow, the glow of a distant galaxy, all delivered by electromagnetic radiation. Unlike gravity, which only pulls, electromagnetism can both attract and repel. Opposite charges attract, like charges repel. This push-pull interplay creates structure on the atomic and human scales. It keeps electrons whizzing around nuclei instead of flying away, and it causes molecules to have the shapes they do, enabling the complex chemistry of life. In the cosmos, electromagnetism governs the behavior of plasma, the hot, charged gas found in stars and nebulae. It sculpts the beautiful filaments of glowing gas in nebulae and the majestic arcs of solar flares rising from the sun. When we see the auroras dancing near Earth's poles, that's electromagnetism at play. Charged particles from the sun guided by Earth's magnetic field into the upper atmosphere, causing molecules to glow. Electromagnetic fields fill space around planets and stars. For instance, the sun's magnetic field, carried by the solar wind, creates a protective heliosphere around our solar system. On Earth, the electromagnetic force is the foundation of technology, electricity, electronics, wireless signals, and biology, chemical bonds, nerve impulses. In a cosmic sense, if gravity is the weaver of the cosmic tapestry, electromagnetism provides the vibrant colors and textures. It gives matter structure and allows the universe to be visible and radiant. The strong nuclear force is the powerful glue of the atomic nucleus. Working at tiny scales, the size of an atomic nucleus or smaller, it binds protons and neutrons together despite the electromagnetic force trying to push positively charged protons apart. Protons naturally repel each other strongly, since like charges repel, and within a nucleus, they are extremely close. It is the strong force that acts like cement to hold these protons and neutrons tightly bound. It is the strongest of the four forces in terms of raw strength, but it operates only across minuscule distances, about the diameter of a proton. Beyond that, its influence drops virtually to zero. Think of it as Velcro that sticks only at very close range. This is fortunate. If the strong force had longer reach, every atom might glom together into one giant nucleus. If it were weaker, nuclei heavier than hydrogen, which contain multiple protons, would fly apart, and the diversity of elements would vanish. In the cores of stars, when temperatures and pressures slam protons together with tremendous force, the strong force takes hold and fuses them. Hydrogen nuclei merge into helium, releasing tremendous energy. This nuclear fusion, governed by the strong force overcoming electromagnetic repulsion, is what makes stars shine for billions of years, converting a bit of mass to energy via EXMC2. The sunlight that warms your face is a byproduct of the strong force at work in the sun's heart, forging helium and releasing energy. Later, in a massive star's life, the strong force will operate on heavier elements. Carbon fuses into heavier elements all the way up to iron. But iron is the end of the line. Fusing iron doesn't yield energy, so in the final moments of a massive star, when its core is iron, the outward pressure stops and gravity causes collapse. The core implodes until the strong force between nucleons, protons, neutrons, and quantum pressures of neutrons say no further, either halting collapse and producing a neutron star, or if the star is massive enough, even the strong force yields and a black hole forms. In either case, the star's outer layers explode in a supernova, scattering heavy elements into space. The strong force in those violent moments forged all elements heavier than iron, gold, uranium, etc., which seed future stars and planets. Thus, the strong force is the creator of elements. It stitched the carbon in your cells, the oxygen in your water, the iron in your blood. Aptly named, it is stronger than electromagnetism at short range, for it must be to bind the nucleus. But outside the nucleus, we never directly sense it. It's confined to the tiny atomic realm. It's the secret fire at the center of matter, unleashed only in rare moments like inside a star or a nuclear reactor or bomb. Without the strong force, atoms beyond hydrogen wouldn't hold together, and the cosmos would be a featureless fog of particles. With it, the richness of atomic matter exists. The weak nuclear force is the most subtle and elusive of the four. It operates within atomic nuclei as well, responsible for certain kinds of nuclear transformations. In particular, it governs radioactive decay and the conversion of one type of particle into another. The weak force is the force of change. Where the strong force holds nuclei together, the weak force lets them transmute. For example, the weak force can turn a neutron into a proton, an electron, and an antineutrino. This is beta decay. This happens in naturally radioactive elements, like a carbon-14 atom decaying into nitrogen-14, emitting an electron. It also happens in the sun. In the proton-proton fusion chain, two protons fuse, and one must turn into a neutron via the weak interaction, allowing them to form deuterium, heavy hydrogen. Without that step, the sun's primary fusion cycle would stall. Thus the weak force, though feeble, is crucial. It lights the stars by enabling fusion and shapes the decay of heavy elements that heat Earth's interior. Radioactive decays of uranium, thorium, potassium contribute to Earth's geothermal heat, driving plate tectonics and volcanoes. The weak force has an incredibly short range, even shorter than the strong force, and is aptly named. It's far weaker than electromagnetism and strong force, stronger than gravity on subatomic scales, but gravity is irrelevant there. We typically notice the weak force only through radioactive decays or in high-energy particle physics experiments. It's carried by heavy W and Z bosons. It doesn't create binding structures. Instead, it allows particles to change identity. It is unique in that it can change a quark's flavor, turning a down quark to an up quark or vice versa, which is how a neutron becomes a proton. We rarely sense the weak force in daily life. It's a behind-the-scenes presence, but it's essential for the evolving cosmos. Without it, the sun wouldn't shine the way it does, and many elements produced in supernovae wouldn't form, because beta decays during those explosions create elements like gold from lighter ones. If the strong force is the builder and electromagnetism the artist, the weak force is the quiet facilitator of change, enabling the cosmic alchemy that gives variety to matter. These four forces together form the infrastructure of reality. Each has its domain of influence. Gravity dominates the astronomical realm of planets, stars, and galaxies. Electromagnetism rules atoms, chemistry, and everyday phenomena. The strong force governs the atomic nucleus and powers stars. The weak force allows the transmutations that underlie both star power and natural radioactivity. They are the threads running through the cosmic fabric, and the fields they generate fill the space around us. Modern physics describes forces via fields and exchange particles. The gravitational field, possibly with gravitons. The electromagnetic field, carried by photons. The strong force field, carried by gluons binding quarks. The weak force field, carried by W and Z bosons. But leaving such technicalities aside, what's astonishing is that these few interactions explain a vast range of phenomena. Consider how these forces all play together in a simple moment. You stand outside on a sunny day. Gravity roots you to Earth and holds our planet in orbit around the sun. Electromagnetism governs the sunlight warming your face and lets your eyes see the world in color. It also keeps the ground solid beneath your feet, electrostatic repulsion between atoms. The strong force long ago fueled the nuclear reactions that produce that sunlight, and even now holds the nuclei of your atoms together. The weak force within the sun allowed protons to turn into neutrons, ensuring the fusion cycle could proceed steadily and power the sunlight. In your body, The weak force is causing a handful of potassium-40 atoms to decay each second, emitting neutrinos that stream harmlessly into space. In that one moment, all four forces are at work seamlessly, and you remain blissfully unaware, simply enjoying the warmth. Throughout cosmic history, these forces guided the formation of structure and the dynamics of change. Gravity drew together the cosmic web and formed stars and galaxies. Electromagnetism made those stars shine and binds atoms into molecules, leading to planets and life. Within stars, the strong and weak forces together forge new elements, which are then spread by supernovae to seed planets and life. We often call them forces of nature, but one might also call them cosmic rules or fundamental interactions, the basic ways pieces of the universe interact. Understanding these forces has allowed us to deepen our comprehension of the cosmos and harness aspects of it for our use. They also inspire a sense of marvel, how elegant that four simple interactions underlie the complexity of the entire universe. Gravity, shaping a galaxy cluster or light from a quasar, 12 billion light-years away, traveling to Hubble's mirror. It's all governed by the same physics that dictates an apple falling or a magnet sticking on a fridge. It suggests a profound unity that from the smallest scales of quarks to the largest scales of galaxy superclusters, the same fundamental forces operate, just with different relative strengths and effects. There are moments in modern physics where we dream of an even more unified picture. Perhaps these four forces were once one, a single force in the extremely hot young universe that later split into four distinct facets as the cosmos cooled. This is the idea behind grand unified theories and attempts to include gravity in quantum theory. Whether nature has such a unified force or not, what stands is that from the grandest cluster of galaxies down to the tiniest atomic nucleus, these four interactions suffice to explain what we observe. When you watch the stars at night, their light reaching you is an interplay of gravity, holding those stars together, and electromagnetism, bringing their light to your eyes, and even quantum effects of atoms, allowed by electromagnetic and strong forces. These forces are the invisible poetry of the cosmos. They make the silent emptiness of space a dynamic arena. Through them, a universe that could have been chaos becomes a symphony of structure and motion. As we understand these forces, we appreciate the finely tuned balance that allows complexity to emerge. With gravity alone, matter would clump infinitely, or not form structure if universe expands too fast. Without gravity, no stars or planets would gather. Without electromagnetism, no atoms or light. Without strong force, no nuclei beyond hydrogen. Without weak, no stellar alchemy creating diverse elements. Our cosmos manages to have them all in just the right mix to give rise to the rich tapestry we see, including us, observers who can reflect on it. Armed with knowledge of the forces, we can now tell the stories governed by them. The deep time tales of stars and galaxies, their births and deaths. These will be our next focus, to see how the cosmos changes over time, how stars live and die, how galaxies evolve, and what fate awaits the universe. Time is the stage on which the forces play, and entropy, the tendency toward disorder, provides an arrow to that time. Let us now unfold the saga of deep time, witnessing the life cycles of stars and the evolving cosmos, told not in equations, but in emotions, as we connect to these distant events that ultimately made our own existence possible. Deep time. In the vast ocean of time, stars are born and die like living things. Galaxies grow and change, and even black holes have life stories. To truly grasp the enormity of cosmic history, we must step outside the human sense of time and enter epochs that dwarf our imagination. Deep time is a realm where 1,000,000 years might pass in the blink of an eye, where the dance of creation and destruction unfolds over eons, with a grandeur at once awe-inspiring and poignant. The life of a star, Picture a dark nebula in a spiral arm of the Milky Way, a cold, dusty cloud light years across, quietly drifting for ages. Within it, a subtle gathering begins, perhaps the shockwave of an ancient supernova, or the pressure of a spiral density wave triggers parts of the cloud to contract under gravity. In those shrinking pockets, gas and dust draw together, atoms crowd and collide, heating up. What was cold and dark starts to glow dull red from the heat of compression. In one such cocoon, at the center of the collapsing cloud, a new light ignites. A protostar is born. It's like a baby star, unstable, convulsing with magnetic storms, gobbling up gas from the surrounding cloud. As it grows, its core becomes denser and hotter until one miraculous moment, hydrogen atoms, squeezed and heated fiercely, begin to fuse into helium. The strong force binds them, the weak force facilitates the fusion, and a torrent of energy is released. Outward pressure from this nuclear fire balances the inward crush of gravity. The star settles into a stable rhythm. It has entered the long, middle chapter of its life, the main sequence. Our Sun is in this phase, shining steadily for about 4.6 billion years, and with roughly 5 billion to go. Throughout the galaxy, countless stars of various sizes share this fate, turning hydrogen into helium in their cores, pouring light and heat into space. They are like the adults of the stellar family, some smaller, cooler, and redder, burning fuel slowly and destined to live extraordinarily long, tens to hundreds of billions of years. Others much larger, hotter, and bluer, burning furiously and living fast. Just a few million years, cosmic mayflies among stars. As time flows, even stars must change. When a star exhausts the hydrogen in its core, the delicate balance tips. Fusion slows. The core begins to contract under gravity and heats up, while the outer layers, freed from the core's pressure, expand outward. For a star like the Sun, this heralds transformation into a red giant. In a deep time vision, one would see the Sun swell many times its current size, perhaps engulfing Mercury, Venus, and even Earth. Its surface cools as it expands, shifting to a luminous orange-red hue, while its core grows hotter and denser until helium can fuse into carbon. For a while, the Sun will juggle new reactions, shining not with its familiar white-yellow, but with the ruby light of old age. It may pulsate gently, shedding its outer layers in concentric waves of gas and dust. In its final breaths, it will cast off those layers entirely, creating a glowing planetary nebula, an expanding shell of gas lit by the hot, exposed core at the center. That core, no longer supported by fusion, will settle into a white dwarf, a hot, dense ember, roughly the size of Earth, but with most of the Sun's mass, slowly cooling over billions of years. The nebula will disperse into the interstellar medium, seeding space with elements the Sun forged, carbon, nitrogen, and more, gifts to the galaxy for future stars and planets. The white dwarf will fade from white to yellow to orange to red to black over trillions of years, a cinder in the darkness. Unless perhaps someday it flares again by accreting matter from a neighbor, as in a nova or supernova, if it had a companion. Such is the quiet finale for a medium star like the Sun. For stars much more massive than the Sun, the end is far more spectacular and violent. These titans, over about 8 solar masses, burn their fuel at a frantic rate, living only a few million years. They blaze hot and blue-white, and after fusing hydrogen to helium in their core, they proceed to fuse helium into carbon and oxygen, then heavier elements in layered shells, neon, magnesium, silicon, all the way to iron. Iron is a dead end. Fusing iron consumes energy instead of releasing it. So a massive star builds up an iron core like ash from a fire. Once the core is largely iron and grows to about 1.4 solar masses, it can no longer support itself against gravity. Thermal pressure and electron degeneracy pressure fail. In literally seconds, the core collapses. Protons and electrons mash together into neutrons, releasing a flood of neutrinos. The core implodes until neutron degeneracy and repulsive nuclear forces halt the collapse abruptly, and then it rebounds. This rebound, aided by neutrino pressure, launches a shockwave outward. The star's outer layers are blown off in one of nature's most cataclysmic events. A supernova explosion, briefly outshining all the billions of other stars in its galaxy. The debris, now rich in those heavy elements beyond iron, which are forged in the incredible temperatures of the explosion, is hurled into interstellar space. This supernova remnant will eventually mix with other gas and perhaps condense into new stars and planets. Meanwhile, the collapsed core remains. If the star's initial mass was moderately high, say 8 to 20 solar masses, the core becomes a neutron star, an object of mind-boggling density, about the size of a city, but with more mass than the Sun, composed mostly of neutrons. It spins rapidly. A newborn neutron star might rotate dozens of times per second, and has a powerful magnetic field, often becoming a pulsar that beams radiation like a lighthouse. If the star was extremely massive, the core collapse overwhelms even neutron degeneracy. No known force can withstand the gravity, and it continues collapsing into a black hole, a region of space-time from which nothing can escape. In either case, something remarkable happens. A once brilliant star ends in a tiny, dark remnant. If a neutron star or black hole is in a binary system, it might later accrete matter and produce X-ray emissions or further explosions, novae, X-ray bursts, etc. This cycle of stellar birth, life, and death is the heartbeat of cosmic evolution. Stars are not eternal. They are born, they mature, they grow old, and they die, often in a way that seeds the next generation. When the first generation of massive stars in the early universe died as supernovae, they produced and scattered the first heavy elements. Those enriched the gas from which new stars formed, including ones smaller, like the Sun, that could host planets with complex chemistry. Indeed, our solar system formed about 4.6 billion years ago from a cloud seeded by earlier stars' deaths, evidenced by radioactive isotopes in meteorites that are products of supernova explosions. Thus, we live in a universe where death begets new life. Supernovae create the raw material for planets and life. Even the gentle expulsion of a red giant's envelope, forming a planetary nebula, returns material to space that can be recycled. Carl Sagan's famous line, "We are made of star stuff," speaks literally true. The carbon in our proteins, the calcium in our bones, the iron in our blood, were all forged in stellar furnaces and spread by stellar deaths. Deep time connects to our very being. The evolution of galaxies. Stars live within galaxies, and galaxies themselves change over cosmic time. Galaxies can be thought of as ecosystems of stars, gas, dust, dark matter, and star clusters, all interacting. Over billions of years, galaxies grow and transform, often through mergers with other galaxies. The early universe likely had many smaller protogalaxies that gradually coalesced into the large galaxies we see today. The Milky Way, for example, has consumed several smaller galaxies in its history, and continues to do so. We see streams of stars in our halo that are remnants of devoured dwarf galaxies. Spiral galaxies like ours likely formed when smaller gas-rich pieces merged, and the combined rotation settled into a disk. Galaxies evolve from one form to another. Two spiral galaxies merging may form an elliptical galaxy, losing their delicate spiral structure in a gravitationally violent embrace and triggering massive bursts of star formation as gas clouds collide and coalesce. Over time, ellipticals, which have little cold gas left after such bursts, become dominated by older, redder stars and have less ongoing star formation. Spirals, if left relatively unperturbed, can keep forming stars as they draw gas inward or accrete from their surroundings, but they too can run low on fuel. Our Milky Way is fated, in about 4 to 5 billion years, to merge with the Andromeda Galaxy, which is currently about 2.5 million light-years away and closing in at 110 km. Despite the enormous number of stars in each galaxy, hundreds of billions, individual stellar collisions are very unlikely due to vast interstellar spaces. However, the gravitational interaction will distort both galaxies dramatically. Over a few billion years, the two will likely settle into a single larger elliptical galaxy, sometimes dubbed Milky Way. Simulations show their beautiful spiral arms will be thrown into chaotic streams. A burst of star formation may occur as gas clouds slam together. Ultimately, a more spheroidal distribution of stars will result. For any creatures alive then, perhaps far descendants of humanity or other intelligences, the night sky will transform. At first, Andromeda grows larger, then the sky fills with a blaze of new star formation and tidal tails of stars, and eventually it settles to a hazy glow of an elliptical galaxy filling the sky. The Sun, by then a red giant or white dwarf, will find itself in a vastly altered cosmic neighborhood. Galaxies also evolve internally. Young galaxies, in the early universe, were often clumpy and irregular, forming stars at high rates. The peak of star formation in the cosmos was around 3 to 4 billion years after the Big Bang. Since then, star formation has generally declined as the big galaxies used up much of their readily available gas. Today, many large galaxies, especially ellipticals, are red and dead, forming few new stars, populated mainly by the aging population born in earlier epochs. Spirals like the Milky Way still form stars, but at a moderate pace. The Milky Way turns about 1 solar mass of gas into new stars per year. Small dwarf galaxies, especially if isolated, may still be forming stars slowly or have spurts of activity when tidal interactions occur. Galaxies can also lose gas. In clusters, where dozens to thousands of galaxies reside, a small galaxy, speeding through the hot intracluster medium, can have its gas stripped, like a breeze blowing leaves off a moving car, a process called ram pressure stripping. This leaves it without fuel for new stars, turning a blue spiral into a reddish gas-poor one. Or a galaxy might have its gas consumed by rapid starbursts or sucked into a central black hole's accretion disk, active galactic nucleus, again quenching star formation. We observe many cluster galaxies that have this quenched appearance. Speaking of black holes, nearly every large galaxy has a supermassive black hole at its center, with masses from millions to billions of suns. In youth, when gas was abundant, these black holes likely powered quasars and active nuclei, sometimes expelling jets and winds that influenced their host galaxies. The interplay between central black holes and galaxy evolution is an area of active research. These black holes might help regulate star formation by heating or expelling gas, a kind of feedback. Thus, galaxies change both from external events, collisions, interactions, and internal dynamics, using up or losing gas, the effects of supernova and black hole feedback. Over deep time, the population of galaxies shifts. Fewer spirals exist now than in the past. Some have merged into ellipticals, and more ellipticals and lenticulars, disk galaxies without much gas or spiral structure, populate clusters. In the far future, as mentioned, accelerating expansion will isolate groups of galaxies. It's thought that in about 100 billion years, if dark energy remains constant, distant galaxies beyond our local group will have moved out of view, leaving future observers in our locale with only the merged Milky Way galaxy and its satellites visible, effectively a cosmic island, with little evidence of the wider universe's existence. They would see an apparent static cosmos of one galaxy, unaware of the greater cosmic web that we now behold. Black holes and the long future. Among the remnants of deep time, black holes stand as perhaps the most enigmatic. A star leaves behind a neutron star or black hole. Galaxies have supermassive black holes at their cores. Over extremely long times, black holes may become the dominant living things as stars burn out. A typical stellar black hole, tens of solar masses, will persist far, far longer than the current age of the universe. But even black holes aren't forever. Stephen Hawking showed that they slowly evaporate by emitting Hawking radiation due to quantum effects near the event horizon. A black hole, the mass of the Sun, would take 1067 years to evaporate, an almost inconceivable span. Supermassive black holes take even longer, 100 plus years. But on the scale of deep time beyond star-filled eras, after all normal matter decays or is ejected, eventually black holes too will leak away their mass and disappear in a final burst of radiation. So imagine the stages of deep time. Now, the stelliferous era, full of stars shining. In about 100 trillion years, the last stars, likely low-mass red dwarfs and white dwarfs cooling into black dwarfs, will fade, the end of the era of starlight. What follows is sometimes called the degenerate era, the universe populated by degenerate remnants, white dwarfs, neutron stars, black holes, and cold brown dwarfs and planets. Collisions among these remnants could occasionally spark new activity. Two brown dwarfs merging might form a brief red star, or two white dwarfs colliding might ignite a supernova. But overall, it's a slow, dim time. Over quadrillions of years, gravitational encounters will gradually unbind most remaining stellar remnants from galaxies. Stars get flung out into the intergalactic void, one by one. Planets will fall into white dwarfs or be ejected. Eventually, even our Milky Way remnant, whatever it becomes after merging with Andromeda, will lose most of its constituents, and the galaxy as a gravitationally bound system will dissolve. Then comes the black hole era. After 1040 or 1050 years, depending on mass distributions, virtually everything left gravitating in lumps are black holes, from massive ones to possibly an army of micro-black holes, if any were created, though unlikely naturally. They slowly evaporate. The universe is dark, except perhaps for occasional flashes when black holes finish evaporating, or rare collisions between remnants. After an absurdly long time, all black holes evaporate too. We reach the final stage, some call the dark era. Only subatomic particles remain, mostly photons, neutrinos, electrons, and positrons, spread so thin across an ever-expanding cosmos that on average years of travel would be required to hit another particle. The temperature everywhere will be effectively absolute zero, apart from quantum fluctuations. The cosmos will have reached maximum entropy, no available free energy to do anything, essentially a quiet heat death. This long view, from bright Big Bang to faint heat death, is mind-bending. It makes our era of galaxies and stars and life seem like a fleeting springtime in the cosmos. And indeed, it is. Yet knowing this timeline can inspire an even greater appreciation for the now. We live in a special time when the universe is full of light and complexity. The deep future, though bleak in prospect, is fortunately trillions of times farther away than the current universe's age, so for all practical purposes, the cosmos will remain lively far, far longer than it has existed so far. Deep time narratives invite us to face both the resilience and impermanence of the cosmos. Stars die, but their remains fertilize new stars. Galaxies collide destructively, but forge new stars in the process. Even black holes might eventually die, but perhaps releasing whatever information they held. Through an emotional lens, these are stories of cosmic reincarnation and renewal, followed eventually by an end of things. An arc with a beginning and end, just as mythologies had, but on incomprehensible scales. To an immortal being watching eons pass, the universe would appear as a vast garden. Stars bloom like cosmic flowers, some short-lived and brilliant, others steady and enduring, then wither, their substance becoming the seeds of new blooms. Galaxies grow by gathering these blooms, sometimes pruning each other in collisions, and eventually, many go to seed themselves as diffuse clouds. The garden analogy falters by the end of time, when darkness covers all. But by then, the garden had given all it could. For us, understanding deep time is at once enlightening and sobering. It contextualizes our brief lives in something far larger. It reminds us that change is constant. No arrangement of matter lasts forever. Yet it also shows how creative the universe has been in the time allotted, going from near uniform gas to conscious beings pondering it all. Now, with a grasp of deep time's canvas, we can zoom back to our human scale and ask, how do we, conscious flickers in this vast unfolding, fit in? The next chapter turns to the emergence of something arguably as remarkable as any galaxy, consciousness, which allows the cosmos to reflect on itself. Scale. As we zoom from the cosmic to the minute, we encounter a remarkable truth. Patterns repeat and echoes sound across vastly different scales. The universe is structured hierarchically, from subatomic particles up through atoms, molecules, planets, stars, galaxies, and the cosmic web. And while each layer has its unique phenomena, sometimes the small and large reflect each other in surprising ways. Imagine scaling down from human size. Shrink 1 billion times. You stand at the edge of an atom, electrons whizzing in a cloud around a tiny nucleus. The nucleus, if you peeked in, is itself a swarm of protons and neutrons, bound tightly by the strong force. Dive further. Inside a proton, you'll find quarks darting amid a sea of gluons. This is a world measured in femtometers, 10 to 15 me, and less, a far cry from everyday scales. Now zoom out, past human scale to planetary and beyond. The Earth orbits the Sun at 150 million km. The Sun orbits the center of the Milky Way, 27,000 light-years away, along with hundreds of billions of other stars. Our galaxy, 100,000 light-years across, is one of perhaps 100 billion in the observable universe. The largest coherent structures we see, walls of galaxies and voids, span a few billion light-years. That's a factor of about 10,040 from the Planck length, 10 to 35 maths, believed to be a fundamental scale of quantum gravity, to the observable universe's diameter, 10 to 27 maths. Yet through this immense range, the same fundamental principles operate. Gravity holds planets in orbit much as it holds galaxies in clusters, just with different relative influences of other forces. Electromagnetism binds an electron to an atomic nucleus and similarly governs the structure of a star via plasma interactions. The forces of nature are scale-blind. They work everywhere, with only their effects modulated by environment. The small and the large often mirror each other. Consider a hydrogen atom, a tiny nucleus with electrons in orbit, historically likened to a miniature solar system. That analogy isn't perfectly accurate. Quantum mechanics shows electrons are in fuzzy probability clouds, not neat orbits. But the structural motif of a central mass with orbiting bodies recurs. Electrons around nuclei, moons around planets, planets around stars, stars around galaxy centers. The binding forces differ, electromagnetic versus gravitational, but the resulting patterns have a visual resonance. A spiral galaxy with its arms may evoke the swirl of water down a drain, or the spiral of a hurricane, not because they are caused by the same reasons, gravity versus pressure and Coriolis forces, but because rotating systems often settle into spirals to conserve angular momentum and form density waves. One fascinating comparison: the cosmic web of galaxies and the network of neurons in a brain have been noted to share similar filamentary structures. One is billions of light-years across, the other confined to a skull, but both are vast networks shaped by growth rules. A 2020 study even quantified similarities in the distribution of matter in the cosmic web and neural networks. While obviously the physics differ, the abstract analysis of connectivity showed parallels in complexity. It's a reminder that complexity can emerge from simple rules at multiple scales, sometimes yielding convergent structures. Our sense of scale is very limited to the human range. We measure in meters and seconds suited to our everyday life. But the universe extends far above and below those. A cosmic perspective forces us to accommodate scales where our intuition fails. It's mind-bending that an atomic nucleus, with its protons and neutrons, is as small relative to us as the sun is large relative to us. We sit roughly in the middle of logarithmic scales, about 10 2 meters in size. On a log plot from the Planck length to the universe, humans are not far from center. In a way, we have 1 foot in the micro-world. We can examine things as small as molecules and atoms with effort, and 1 foot in the cosmic. We can see galaxies and clusters with our telescopes. Perhaps this accident of scale is what allowed us as a species to comprehend things far beyond our direct sensory realm. We evolved in a world where both small and large phenomena affected us, from grains of sand to the cycling sun and moon, giving us curiosity in both directions. And indeed, modern science is a triumph of exploring both the very small and very large. By going down to subatomic scales, we've uncovered the fundamental particles and forces enabling technologies like electronics and nuclear energy. By going up to cosmic scales, we've discovered the Big Bang, cosmic expansion, and the age of the universe. The fact that the human mind, a small-scale object itself, can grasp scales 10-20 times smaller and 10-20 times larger than itself is astonishing. It's a testament to mathematics and imagination that we can conceptualize things so far outside direct experience. Another connection across scales is that the very large was seeded by the very small. Quantum fluctuations, random tiny variations at the subatomic level, during the epoch of inflation in the extremely early universe, were blown up to macroscopic size, laying down the pattern for the cosmic web. Thus, the distribution of clusters and voids we see today is in part a fossil record of quantum events in the first 10 to 30 seconds of the universe. The microscopic shaped the telescopic. This is almost poetic. The initial graininess on the quantum level became the literal grains, galaxies, in the cosmic structure. Conversely, understanding large-scale processes often helps reveal small-scale physics. For example, observing the nuclear reactions in the Sun via neutrinos and helioseismology confirmed our knowledge of particle physics, like the properties of neutrinos. The solar neutrino problem and its resolution in neutrino oscillations showed neutrinos have mass, a small-scale property discovered by looking at a star. Cosmology data, like the microwave background and element abundances, provide evidence for particle physics phenomena, like the existence of relativistic species, neutrinos, in the early universe. In summary, the cosmos is truly fractal-like in its wonders. Patterns and principles iterate, and insight at one scale often informs another. We find ourselves at an intermediate scale, but equipped with tools and reason to traverse the extremes. By doing so, we realize that we are not isolated at our scale. We are made of subatomic particles, and we orbit a star in a galaxy. We contain multitudes of atoms, and we are part of something larger, the universe. Embracing this multi-scale reality adds to our awe. The next time you hold a salt crystal, consider that within its tiny cubic structure lies a microcosm of electromagnetic forces and quantum rules, not entirely unlike the gravitational lattice of galactic clusters spanning millions of light years. The salt's sodium and chlorine atoms form a repeating pattern, just as galaxies form a weave in space. Patterns at vastly different scales can still rhyme. Now, stepping back from scale and structure, we venture into what might be the strangest aspects of the cosmos. Those that challenge our understanding not just of size or shape, but of reality itself. Black holes that warp space-time, mysterious dark matter and dark energy that we detect only indirectly, hypothetical wormholes that might tunnel through space-time, and other unknowns that remind us how much more there is to learn. It's time to explore the strange cosmos, the mysterious components and possibilities that push the boundaries of known physics. The strange cosmos. For all that we have learned, the cosmos still guards many secrets. In fact, the more we've discovered, the more we've realized how much lies in darkness, hidden from direct perception. The night sky we see, with its stars and galaxies, is only a thin slice of reality. The rest is filled with mysteries, unseen matter and energy, space-time oddities, cosmic phenomena that challenge our intuition. Among these enigmas are black holes, dark matter, dark energy, and the hypothetical wormholes and parallel universes that tantalize physicists and philosophers alike. These are the strange elements of the cosmos that make it not just vast, but deeply mysterious. Black holes, the abyss of space-time. Perhaps nothing in the universe is as foreboding and fascinating as a black hole. Imagine a star 10 times the sun's mass reaching the end of its life. Its core fuel spent, it collapses under its own weight. If nothing stops the collapse, and for a massive core nothing will, it shrinks past the formation of a neutron star, past any known stable form, to a point, a singularity, of seemingly infinite density. All that mass is now concentrated in zero volume, and gravity around it becomes so intense that within a certain radius, the event horizon, not even light can escape. A black hole is born, an object with a one-way surface. Cross the event horizon, and you cannot return or send a message out. To the outside world, you effectively vanish. Black holes take our understanding of physics to the edge. According to Einstein's general relativity, mass curves space-time. A black hole is an extreme curvature where space-time essentially pinches off. Time and space swap roles in a sense. Moving forward in time inevitably carries you inward toward the singularity if you're inside the horizon. Quantum physics adds further mystery. At the event horizon, quantum effects can create particle pairs, leading to Hawking radiation, meaning black holes aren't completely black. They glow faintly and lose mass over time. We have strong evidence black holes exist. Stellar black holes announce themselves by gravitational effects on companions and by emitting X-rays when consuming gas. We have imaged the shadow of a 6 billion solar mass black hole in galaxy M87 via the Event Horizon Telescope, seeing a ring of light from hot gas and a dark center where the hole's gravity prevents light from coming directly to us. We see stars at the center of our Milky Way whipping around an invisible 4 million solar mass object at speeds of thousands of km/h. Definitely a supermassive black hole. So black holes are not just theoretical. They are out there. Commonplace, in fact. Every large galaxy likely has one, and many stellar remnants become black holes. They distort reality around them. Clocks near a black hole run slower relative to far away. To a distant observer, a clock falling toward a black hole appears to tick ever slower and essentially freeze at the horizon, though the clock itself experiences falling through normally. If you fell in, past tidal forces ripping you apart, if it's a small hole, you might have some time to observe near the singularity, but ultimately you'd be crushed, and what's inside the horizon is cut off from our universe, so it's like you've left our reality. Black holes are strange because they present a breakdown of our laws. A singularity is a sign that general relativity gives infinite results, meaning the theory breaks down there. It's expected that quantum gravity, a future theory uniting GR and quantum mechanics, will resolve what happens at the core. Do singularities exist, or are they replaced by something like a quantum fuzz or bounce? Also, do black holes destroy information? Quantum theory says information, the specifics of matter that fell in, should be preserved in some form. This has led to the famous black hole information paradox. Many physicists now think information does escape in subtle form via Hawking radiation or is stored in correlations, meaning black holes might not erase information entirely, no cosmic delete button, just very scrambled output. Even more exotic is speculation that a black hole could connect to another region of space-time, a wormhole. In principle, the mathematics of GR allow an Einstein-Rosen bridge connecting two black holes, or a black hole and a hypothetical white hole, essentially a tunnel. But such wormholes, if they exist, would be unstable. They'd pinch off unless held open by negative energy, exotic matter. We have no evidence wormholes exist naturally. They might be purely theoretical or require technology far beyond us to stabilize. Still, they captivate the imagination as cosmic shortcuts or even time machines, since wormholes potentially could allow travel back in time, raising paradoxes. Dark matter, the hidden mass. In the 1970s, astronomer Vera Rubin measured how fast stars orbit in the outer parts of spiral galaxies and found something odd. They were moving as fast as stars closer in. According to Newtonian gravity, stars far from the galactic center should orbit more slowly if most mass is concentrated in the center, like planets in the solar system. Instead, galaxy rotation curves flatten out, indicating there's much more gravity, and hence mass, in the outskirts than can be accounted for by visible stars and gas. Similarly, clusters of galaxies have galaxies moving too quickly to be held together by the visible mass alone, and gravitational lensing, the way clusters bend background light, indicates more mass than seen. The conclusion: most of the matter is unseen, dubbed dark matter. Dark matter seems to interact gravitationally, but not, or extremely weakly, via electromagnetic or nuclear forces. It doesn't emit, absorb, or scatter light, hence dark. It's not made of atoms. It's something else, likely some kind of particle left over from the Big Bang that we have yet to detect in the lab. It outweighs normal matter roughly 5.1 in the universe. It's the scaffolding on which galaxies formed, as discussed in the cosmic web. Without dark matter, our models struggle to form galaxies as observed, and structures might not hold together. Despite decades of trying, we haven't directly observed dark matter particles on Earth. Various underground detectors have looked for them hitting nuclei, without confirmed success yet, or created them in colliders. We infer their existence from their gravitational effects. The leading hypothesis is that dark matter is some kind of WIMP, weakly interacting massive particle, left from the early universe, or possibly an axion, a very light particle, or something more exotic like a dark sector with its own forces. But so far, it's a shadowy presence, clearly there, yet elusive. Some have proposed alternative gravity theories, like MOND, modified Newtonian dynamics, or various relativistic extensions, to eliminate the need for dark matter by changing how gravity works at galaxy scales. While these can fit some galaxy rotation curves, they struggle with cluster lensing and the cosmic microwave background data that strongly support the dark matter paradigm. The simplest consistent explanation remains a dominant component of unseen matter. So, to an extent, we live in a shadow universe. Only about 1/6 of matter is the familiar atoms that make up stars, planets, and us. The rest, plus an even larger fraction in dark energy, which we'll get to, is hidden. It's humbling. All the glowing galaxies are like a froth on a vast, dark ocean of matter. Without that ocean, though, the froth wouldn't exist. Dark matter's gravity was essential to gather normal matter into galaxies. Dark energy, the runaway expansion. In 1998, two teams measuring distances to far supernovae made a shocking discovery. Distant type Ia supernovae were dimmer than expected, indicating they were farther than they should be if the universe's expansion were slowing down. Put simply, the expansion of the universe has been speeding up in the last few billion years. This was the opposite of what most expected. Gravity from matter should slow expansion. The cause was dubbed dark energy, a mysterious form of energy that fills space and drives accelerated expansion. It's often associated with the cosmological constant, L, concept that Einstein once introduced and famously discarded as a blunder when he thought the universe was static, now revived as a physical reality. Dark energy is even more enigmatic than dark matter. It constitutes about 68% of the universe's total energy content. We don't know what it is. If it's a true cosmological constant, it's an inherent property of space. Every cubic meter of vacuum has some fixed tiny energy, around 6 by 10 hours to 10 joules, that doesn't dilute as space expands. So as space grows, more vacuum means more total energy, causing expansion to accelerate. Alternatively, dark energy might be a field that can change over time, sometimes called quintessence, or something even more exotic, like an effect of other dimensions or a flaw in GR on huge scales. So far, all observations, supernova, cosmic microwave background, large-scale structure, are consistent with dark energy being a constant property of space, with an equation of state parameter, WL1, in cosmological terms. If it remains so, the fate is an ever-accelerating expansion. Galaxies outside our local group will recede faster and faster until they become unreachable and eventually invisible. Dark energy seems to have become dominant a few billion years ago. Prior to that, matter's gravity was slowing expansion. But as the universe expanded, matter diluted, density dropping as volume increases, whereas dark energy, as a constant density, did not. Eventually, matter's influence waned and dark energy took over, causing expansion to accelerate. Why dark energy has the value it does is a huge puzzle. Quantum zero-point energy calculations naively predict a cosmological constant, 10^120 times larger, which would have blown the universe apart instantly after the Big Bang. A gross discrepancy, one of the biggest in physics. Something, perhaps a cancellation mechanism we don't understand, leaves a small residual that is our dark energy. That's a major unsolved problem. If dark energy is constant, the universe will approach a de Sitter state, exponential expansion forever. If it's not constant, who knows? Some theorize dark energy could decay or even reverse, leading to a big crunch or oscillation, but no evidence of such behavior yet. So we live in a universe where about 95% of its content is in two invisible forms, dark matter and dark energy. It's as if we have a book where only some letters are visible and the rest are in invisible ink. We're trying to read the story from the few visible letters and a lot of blank spaces. Yet the visible letters, stars, galaxies, etc., give us enough clues through their dynamics and arrangements to infer what's missing. Wormholes and other wild ideas. The notion of wormholes, shortcuts through space-time, has long captured imagination. Solutions of Einstein's equations, like the Schwarzschild wormhole, which is the non-traversable mathematical connection in a black hole solution, or the traversable Morris-Thorne wormholes that require exotic matter with negative energy, indicate such tunnels are not forbidden by general relativity outright. But whether nature actually makes any is unknown. If cosmic strings, defects in spacetime from early universe phase transitions, or certain quantum fluctuations occurred, some think it might be possible a few wormholes were spawned, but they'd likely collapse quickly or be extremely tiny. No evidence exists for any. If one could stabilize a wormhole, it could allow faster than light travel, effectively by taking a shortcut, or even time travel, depending how the wormhole mouths move relative to each other. But physics as we know it strongly suggests causality violations are not allowed. Time travel leads to paradoxes, though closed time-like curves can exist in theory. Most physicists suspect some deeper principle prevents actual time machines. Another wild idea: maybe our whole universe is a patch inside a larger multiverse, where other universes have different physical constants or particles. Inflation theory suggests space might be much larger than our observable part, possibly with other bubble universes disconnected from ours. If so, maybe constants like gravity's strength or protons' mass could vary in those bubbles. That could partially explain why our constants are tuned for life, anthropic selection from many universes. But this remains speculative and arguably untestable. We can't observe other universes if they're truly disjoint. Some signatures like colliding bubble universes might imprint something in our cosmic background, but none clearly seen. It might be that what we call constants of nature are not fixed in space-time either. There are studies testing if, say, the fine structure constant, electromagnetic strength, or electron-proton mass ratio has changed over cosmic time by analyzing ancient light. So far, results are mostly consistent with no change, or changes so slight they remain debated. If any drift exists, it's very tiny, meaning the laws today were essentially the laws 10 billion years ago. All these strange aspects, wormholes, multiverses, varying constants, stretch the boundaries of the known. They are at the edge of science and veer into philosophy at times because they're hard to verify or falsify. Still, exploring them is valuable. It expands our conception of what might be possible and forces us to confront the assumptions in our accepted theories. Embracing mystery. Confronting the strange cosmos instills humility. We see that our knowledge, while vast compared to the ancients, may still be scratching the surface. We uncovered dark matter and energy by their gravitational footprints, but we don't yet know their identities. We theorized black holes from relativity, then found they are real astrophysical objects, yet at their core lies the need for a new theory, quantum gravity, to understand singularities. We use quantum mechanics and relativity daily in our devices and GPS, yet their reconciliation into one framework eludes us, hinting at deeper layers of reality. The strange elements of the cosmos are clues that the story isn't finished. There are chapters of physics yet to be written, perhaps by future generations. And yet, rather than these unknowns making the universe seem alien, they can also inspire a sense of being part of a grand quest. We alive today are among the first generation to know that dark matter and dark energy exist. Perhaps one day a child today will solve the riddle of dark matter in a lab experiment or theory. We stand on a threshold where the cosmos is telling us there's more here than meets the eye. In grappling with the strange, we also find a reassuring continuity. Every time our view expanded or was challenged by Copernicus, by Hubble, by dark energy's discovery, we eventually integrated it and found our understanding actually deepened and often benefited humanity. Imagine modern tech without quantum mechanics or relativity, which were once strange new ideas. So there is faith, born of experience, that confronting the unknown is worthwhile, and reality, however strange, is ultimately comprehensible, as Einstein mused. Now, having explored the structure and mysteries of the external cosmos, we turn inward to perhaps the most remarkable outcome of cosmic evolution, ourselves, conscious beings capable of reflecting on the cosmos. We examine how the universe, through life and mind, has awakened to itself, and what that means for meaning and perspective. Consciousness. At some point in cosmic history, the cosmos became aware of itself, on at least one planet and perhaps countless others, a collection of atoms organized in such a way that it could ponder the very stars that made its constituents. This phenomenon, consciousness, is the most complex and mysterious form of order we know. Through us, and beings like us, the universe has eyes to see and minds to contemplate its own vastness. Carl Sagan put it poetically, "We are a way for the universe to know itself." The journey to consciousness was gradual and took billions of years on Earth. Simple life emerged at least 3.5 billion years ago in Earth's oceans. likely as self-replicating molecules that became enclosed in membranes, primitive cells. These life forms could sense and respond. Even a bacterium will move toward nutrients or away from harm. That's a rudimentary form of awareness, not thought, but biological feedback. Multicellular life allowed differentiation, specialized cells for sensing, like light-sensitive patches that became eyes, and for processing, simple neural nets. By the Cambrian explosion, 540 million years ago, complex animals with eyes and nervous systems filled the seas, presumably experiencing basic perceptions. Fast forward, vertebrates developed more complex brains. Some lineages crawled onto land. In mammals, the brain's cortex expanded, enabling memory, learning, and emotion. At some indeterminate point, early humans or their ancestors achieved self-awareness, an ability not just to feel or learn, but to know that they know, to reflect on one's own existence. Consciousness is hard to define but intimately known to each of us. It's the subjective experience of internal and external reality. It's the I am behind your eyes, the experiencer of your life. Scientifically, we map its correlates, brain patterns, neural oscillations, integrated information, but we don't truly understand how the grey matter of the brain produces the bright light of consciousness. This is the hard problem of consciousness. Yet, it undeniably does, at least in humans, and likely other animals to varying degrees. From a cosmic perspective, consciousness is profound because it seems qualitatively different from unconscious matter. The ingredients that make a human, oxygen, carbon, hydrogen, nitrogen, calcium, etc., are common in the cosmos, in air and rock and sea, but arrange them in the exquisite complexity of a living cell, then an organ, then a brain, and something novel emerges: mind. It raises a question. Is consciousness a fundamental aspect of the universe? Some philosophers and physicists have toyed with panpsychism, that consciousness might be a property of matter under certain conditions. Or is it an emergent phenomenon requiring a certain level of complexity? Either way, the potential for mind was built into the cosmos from the start, in the sense that the laws of physics allowed matter to self-organize into conscious forms. When the universe was a hot plasma, it had no structures at all, let alone life. But it cooled, matter clumped, stars forged heavier elements, planets formed with complex chemistry, life sparked and evolved, and eventually, those ancient atomic nuclei, born in the hearts of stars, became part of a thinking being that can look back and say, "Wow, I come from the stars." The cosmos became aware of its origins through our minds. This confers a sense of purpose, in a way. Not an externally assigned purpose, but a role we naturally play. We are the cosmos, in one of its latest evolutionary phases, marveling at itself. When we discover things about the universe, it is literally the universe discovering itself. Our joy of comprehension is the universe taking joy in self-comprehension. Consciousness also heightens the emotional stakes of cosmic knowledge. Without conscious beings, the grand universe simply is, with no one to admire a nebula or fear a black hole. With consciousness, beauty and terror enter the scene. Think of the first humans fearful of eclipses or awestruck by the Milky Way. The cosmos evokes feelings now because we feel. Through us, the universe has emotion and meaning, at least locally. A nebula is not objectively beautiful, but we find it so, giving aesthetic dimension to existence that wouldn't exist without minds. Many scientists and philosophers suspect life and possibly consciousness might not be unique to Earth. If biology is a natural outcome on wet, rocky worlds under the right conditions, and evolution often fosters intelligence given enough time, then perhaps the cosmos teems with other conscious beings. They may not be human-like, but they could wonder and seek as we do. Perhaps the universe has many centers of consciousness scattered among the galaxies. A kind of cosmic self-awareness shining in many places. Or perhaps not. Maybe intelligent life is extremely rare. We don't know yet. Either answer, teeming life or cosmic solitude, is profound. If we are among many, what a grand community awaits discovery, though distances are forbidding. If we are alone, or nearly so, what a precious flame of awareness we bear, and what responsibility to not squander it. Consciousness gives the universe a way to know time in a meaningful way too. Without minds, time just passes. With minds, the passage of time is felt. We have memory of the past and anticipation of the future. We seek patterns and thus uncover cosmic history, like figuring out the Big Bang, and cosmic future, heat death or other fates. In a sense, by becoming aware of deep time, we have extended the reach of consciousness to the entire lifespan of the universe. Mentally, we travel to the beginning and to hypothetical ends. The universe through us can contemplate its entire existence, almost like how we as individuals reflect on our own lives. There is also a contemplative aspect. Many find that recognizing we are the universe coming to consciousness can be spiritually meaningful. It collapses the divide between me and world. In a cosmic sense, the distinction is indeed arbitrary. We're made of the world and return to it. As conscious beings, we can feel empathy not just to other living things, but to the stars and the atoms, feeling a unity with all. Some spiritual traditions echo this scientific truth. We are one with the universe. As we move forward, conscious of our conscious role, we might ask, what next for the cosmos and consciousness? Will our awareness fade when humanity, or life, ends, or will it spread? Some dream of humanity expanding to other planets, carrying consciousness further through the cosmos. In doing so, giving the universe more places where it can reflect on itself. Others consider that artificial intelligence might carry consciousness, or at least intelligence forward, even if biological life fails. It's a speculative territory, but the point remains. Through our minds, the universe has reached a level of self-reflection, and what we do with that is, to some extent, up to us. Having considered mind and meaning, let's pull back one last time to the broadest perspective. Is our universe the only one? Or could there be a multitude, a multiverse? And is the structure of reality fundamentally made of something like information or math, rather than tangible matter? These are deep questions at the intersection of physics and philosophy. We touch on them briefly, as they color the ultimate context in which our cosmos might reside. The multiverse. Is our universe unique, or one of many? For ages, universe meant all there is. But modern physics has opened the door to the idea that our universe might be a bubble in a froth of countless universes. A multiverse. This concept arises from several lines of thought. One is cosmic inflation, the idea that a fraction of a second after the Big Bang, space expanded exponentially fast. Inflation theory, in many versions, suggests that inflation didn't end everywhere at once. It ended in patches, like our universe, while other regions kept inflating, budding off other bubble universes. If eternal inflation is correct, our universe may be one domain among an indefinitely large, possibly infinite number of domains, each a universe in its own right, with potentially different properties. Another motivator is fine-tuning. We observe that certain fundamental constants, like the strength of electromagnetism or the dark energy density, have values in a narrow range that allows complexity, galaxies, stars, life, to exist. It's puzzling why they have just those life-permitting values. One possible explanation is the anthropic principle combined with a multiverse. If indeed many universes exist with varying constants, we naturally find ourselves in one of the minority that by chance has the right conditions for observers, because only such universes get observers. It's like we shouldn't be surprised to live on Earth rather than on Jupiter. Only Earth had the proper conditions for our kind of life. Similarly, Maybe only a small fraction of universes have viable physics for any form of complexity. And of course, we must be in one of those. If the multiverse idea is true, reality is much bigger than we can see. Our observable cosmos, the 93 billion light-year bubble of space we can currently observe, would be just a tiny patch in an inconceivably vast inflating space that contains other bubbles beyond our horizon. We cannot directly communicate with or travel to those other universes. Space between us and them is still inflating, or they're causally disconnected. But their existence would answer some otherwise intractable why questions by essentially saying everything happens somewhere. We see what we see because those conditions are necessary for us to exist. In some multiverse scenarios, the basic laws might differ. Perhaps one universe has a slightly stronger, strong force, which might mean no hydrogen, all protons fuse into heavier elements quickly, or a slightly weaker electromagnetic force. Maybe stars can't form because fusion won't ignite. There might even be universes with different numbers of spatial dimensions or different particle types. The possibilities are vast in principle. We don't know if physical constants can vary like that. But string theory, for instance, predicts a landscape of possible vacuum states with different properties, and eternal inflation could populate different regions with different vacuum states, hence different constants and particle physics. It's almost a philosophical question. Are these other universes real if we can never observe them? Some say if a theory that predicts them also robustly predicts things we can observe, and the theory is validated, then we must accept whatever else it entails, like unseen universes. Others argue that non-disprovable entities are not within science's remit. Currently, the multiverse is a hypothesis, intriguing, sometimes seemingly implied by theories but not confirmed. Parallel to the cosmological multiverse is the idea from quantum mechanics of the many worlds interpretation, that every quantum event that has multiple outcomes, electron goes left or right, spawns branches of reality for each outcome. In that view, all possible histories consistent with quantum probabilities play out in a vast branching of universes. This is a different beast than the inflationary multiverse. These universes occupy the same space but in different quantum branches, rather than separate bubbles of space. But interestingly, both ideas paint a picture of numerous alternate realities. If both were true, it could be an unimaginably enormous collection of universes, bubble universes, each with internal branching quantum worlds. These ideas challenge our notion of uniqueness. It might make one feel small. Not only are we one tiny planet in a vast universe, but our entire universe might be one grain of sand on an endless cosmic shore. But one can also find it empowering. If indeed our universe is rare enough to permit life, how lucky we are to experience it. If universes are countless, then the creative potential of reality is truly without limit. Whatever can happen will happen somewhere, perhaps many times over. One might ask, how does multiverse thinking affect daily life or meaning? Perhaps not much. True or not, it doesn't change the tangible universe we interact with. But it adds another layer to the grand perspective, maybe even our entire cosmic cosmos, a journey through space and time. The sun rises in silence, but its presence is a chorus that has echoed through every age of life on Earth. Every morning, its gentle light spills over the horizon and washes the world in gold. In that light lies an ancient promise: warmth to nourish the living, energy to spark the green fuse of plants, and comfort to chase away the chill of night. For as long as creatures have walked under the sky, they have felt the sun's touch and known instinctively that this brilliant star is the giver of life. Yet the sun is more than a kindly nurturer. It is a colossal power, a raging sphere of fire suspended in the darkness of space. From across the cosmic void, it seems tame, a perfect golden disk that rises and sets with reliable grace. But up close, it is wild and untamable, a seething ocean of plasma and magnetic fury. It holds Earth in its grasp, guiding the dance of days and seasons. And it could, in an instant of cosmic anger, scorch our world lifeless. The same sun that gently warms our faces can also unleash deadly radiation and storms of charged particles. It is a giver of life, and it can be a destroyer of worlds. Our ancestors revered the sun as divine, calling it by many names and worshipping its life-giving light. They built great stone circles and temples aligned to its rising, celebrated when it climbed high in summer, and feared its waning in winter. In rare moments, when the sun vanished in a daytime eclipse, they watched in dread and awe as day turned to twilight, praying for the light to return. They sensed its dual nature, its generosity and its danger, even without knowing the science. We now understand that the sun is a star, one among countless others in the galaxy. But to us, it is unique. It is our star, the hearth of our solar system, the steady heartbeat of our cosmic home. It beats silently, a deep thrum of nuclear fires and magnetic pulses that we cannot hear, but that sustains us nonetheless. Every ray of sunlight is a note in that silent symphony, a connection between our small lives and the vastness of the cosmos. Consider this. The light that caresses your skin today began its journey at the core of the sun long before you were born. The warmth on your face is the end of a story that started deep in a stellar furnace. The sun bridges our brief human moment and deep cosmic time. It links the atoms in our bodies to the atoms in distant stars. In its light, we find both our origin and our destiny. We stand in the glow of a cosmic engine, often unaware that above us, a star's turbulent heart is burning and beating ceaselessly. To truly know the sun, we must journey into its very heart. Let us leave behind the blue of our sky and travel inward into the blinding brilliance, into the inner sanctum of our nearest star. What we find there is both humbling and wondrous, a story of creation and destruction, of light and darkness, of a star's life from birth to death. It is, in many ways, the story of ourselves, written in the language of light. Imagine plunging through the sun's surface and journeying toward its center. As we descend, the light intensifies and the heat becomes unimaginable. Deep inside, at the very core of the sun, we enter a realm of staggering pressure and temperature. Here in this stellar heart, hydrogen atoms are crushed together so tightly that they fuse into helium. In that act of fusion, a tiny bit of matter transforms into pure energy, an alchemy that powers the sun. This is the engine of creation hidden in the sun's core. Every second, an immense burst of energy is released, radiating outward to keep the star shining. Gravity presses inward relentlessly, trying to collapse the sun under its own weight, but the fury of nuclear fusion pushes outward, holding the star up. In this balance between gravity and fire, the sun's core burns steadily, a sphere of blazing plasma denser than solid iron and far hotter than any furnace on Earth. The core is a place of extremes beyond our experience. Its light is born in blinding abundance, yet none of that brilliance escapes directly. Only ghostly particles called neutrinos slip away unhindered, streaming out from the core and passing through the sun's layers, and even through our bodies on Earth, as though nothing were there at all. They are the silent heralds of the sun's heart, whispering of the nuclear fires within. Moving outward from the core, we enter the radiative zone, a vast internal layer where the energy from the core migrates slowly outward in the form of light. Here, photons of radiation ricochet through a dense maze of atoms. A single particle of light, born in the core's fury, may bounce countless times from one atom to another, absorbed and re-emitted in an endless random walk. The plasma in this zone is so opaque and crowded that progress for any ray of light is agonizingly slow. Ages pass as the energy inches its way outward. What we eventually perceive as sunlight on Earth has spent eons fighting its way through this hot, stifling labyrinth. In these deep regions of the sun, energy is transferred not in a simple beam, but like a traveler lost in a thick forest, zigzagging gradually toward freedom. Eventually, the character of the sun's interior changes. Further out, the stellar plasma becomes cooler and less dense, and it can no longer transport energy purely by the random diffusion of photons. At this point, a new process takes over: convection. We have entered the convective zone, the sun's outermost interior layer, where heat is carried upward by the motion of the gas itself. Picture an immense cosmic cauldron boiling slowly. Hot plasma from the layers below becomes buoyant and rises toward the surface, carrying energy with it. Upon reaching higher, cooler regions, it loses heat, becomes denser, and sinks down again to be reheated. These rolling currents form giant looping cells of plasma the size of continents, rising and falling in rhythmic surges. Through the convective zone, energy that once took millennia to crawl outward now surges toward the surface in a matter of mere weeks, riding the updrafts of this titanic, boiling motion. At last, the energy reaches the visible surface of the sun, the photosphere. This is the layer where the sun's light finally escapes into space and shines freely across the solar system. To our eyes, the photosphere is the sun's radiant face, a glowing golden disk with a sharply defined edge. Up close, it would not appear smooth at all, but finely textured and ever-changing. The surface seethes with the imprint of the convection below, a pattern of granules, like a vast mosaic of luminous cells. Each granule is the top of a convective plume, a cell of hot plasma rising from the depths. Their centers glow bright and white-hot, where fresh energy wells up, and their edges darken to a deeper amber, where cooler plasma is sinking back down. This granular pattern continually shifts and reforms, as though the sun's face is a living, boiling sea of light. Here and there, the photosphere is marred by dark blemishes, sunspots. These spots are cooler than their surroundings, and so they appear nearly black against the brilliance of the sun's face. A sunspot is born from the sun's magnetic mischief. Intense magnetic fields well up from inside the sun and suppress the hot rising gas, creating a region that is slightly less hot and thus darker. Sunspots can grow to be larger than the entire Earth and may last for days or weeks before dissipating. They are a sign that the sun's magnetism, though invisible, is ever present, knitting itself into the solar surface. We will soon see how these magnetic forces can erupt in violence, but for now, standing at the surface of the sun, we behold a roiling ocean of fire extending in all directions, a vista of constant boiling creation. Peering at the sun's face with sensitive instruments, we find that it is also vibrating subtly. The boiling convection within causes the sun to ring like a resonant bell. Its surface shivers in patterns, waves traveling across and through the sun, making the whole star gently pulse. Astronomers use these pulsations, this music of the sun, to probe its interior, much as one might learn the shape of a bell from the sound it makes. Through this solar symphony, we can discern the flowing currents deep inside, the building magnetic fields, and even hints of the sun's core, all hidden beneath the blinding glare. Rising above the photosphere, the sun's atmosphere continues outward in layers of increasing mystery. Just above the visible surface lies the chromosphere, a tenuous veil of gas that appears as a faint, pinkish glow. Here, the temperature, which had cooled at the photosphere, begins to climb once more. The chromosphere is like the sun's shimmering halo, visible clearly only when the bright photosphere is hidden during a solar eclipse. In those rare moments, it can be seen as a thin rim of ruby light encircling the moon's silhouette. Within the chromosphere, slender jets of plasma called spicules, continually shoot upward, each one ephemeral and short-lived, lasting only minutes before falling back. The chromosphere is a restless transitional zone, a place where the fury from below meets the stillness of space above, and the solar atmosphere prepares for an abrupt and profound change. Above the chromosphere lies the sun's crown, the corona. Faint and otherworldly, the corona is a vast halo of pearly light that surrounds the sun and stretches far into space. It is breathtakingly beautiful and enigmatic, revealed to human eyes only during a total solar eclipse, or through specialized telescopes that block the sun's glare. In those brief eclipse moments, when daytime twilight descends and the moon hides the sun's brilliance, the corona appears as a pale, white aura, etched with luminous streamers and delicate filaments extending in all directions. But the corona is not merely a spectacle of light, it is a furnace in its own right, one far hotter than the sun's surface below. While the sun's photosphere is blisteringly hot, the corona above is unimaginably hotter, a puzzling reversal of what one might intuitively expect. In this outermost layer, the sun's magnetic field rules supreme, shaping the thin gases into graceful loops and arching structures. Great magnetic arches rise high above the sun, filled with incandescent plasma that traces the invisible lines of force. The corona is incredibly thin, its particles so sparse that if you were standing in it, shielded somehow from the heat, you might not even notice the few atoms brushing by. And yet, despite its tenuousness, the corona possesses immense energy and reaches temperatures of such magnitude that scientific instruments must strain to record them. Why does the corona burn so fiercely? It remains one of the sun's lingering mysteries. Perhaps the sun's tangled magnetic fields thrash and snap, heating the gas in a myriad of tiny explosions, or waves of energy ripple outward from the sun's surface, dumping heat into the corona. Whatever the cause, the sun's crown glows with an ethereal fire that science is still striving to fully understand, a reminder that even our well-known star holds secrets at its heights. At the edge of the corona, the sun begins to fade into the darkness of space. There is no sharp boundary where the star ends. Its atmosphere simply thins into the void. Here, the corona gives birth to the solar wind, a ceaseless stream of charged particles, electrons and protons, that flows outward in all directions. The sun, in effect, is always breathing out. Its breath is the solar wind, and it carries a piece of the sun's essence out to the farthest planets and beyond. The gravity that so overwhelmingly confines the core cannot hold these fast, lightweight particles of the corona. They race outward along open magnetic lines, escaping the sun's grip. The solar wind is, in a sense, the sun's extended atmosphere flowing freely into space, filling the solar system like an invisible, ever-expanding bubble. We have now traveled from the sun's core, where matter becomes energy, to the wispy fringes of its corona, where the star dissolves into the broader cosmos. In this journey, we have witnessed the anatomy of a star, its layered realms, each with its own wonders. We have seen the ferocious furnace at its center, the slow upward struggle of light, the boiling convection that brings energy to the surface, the radiant face shining into space, and the crown of fire that reaches beyond the sun itself. Yet the sun is far from a static ball of gas. It is dynamic and alive, its surfaces and atmosphere writhing with magnetic fields and sudden eruptions. To truly understand our star, we must explore these invisible forces that bind and sometimes unravel the sun's material. We must watch as the sun's calm radiance is punctuated by storms, blazing flares, erupting prominences, and billowing clouds of plasma that can span millions of miles. It is time to examine the sun's magnetic heart and the space weather it breathes into the solar system. Beneath the sun's bright face lies an unseen web of forces that drives its most dramatic behavior. The sun is a giant magnetic dynamo. As it spins on its axis and its plasma churns, it generates magnetic fields that thread through its interior and arch out into space. Imagine lines of unseen force looping out from the sun's depths, arcing high above the surface and diving back down. These magnetic field lines become twisted and tangled by the sun's constant turning and boiling. Where they burst through the surface, they drag up or suppress hot plasma, creating the dark sunspots we see freckling the photosphere. Every feature we observe on the sun, its spots, its flares, its glowing coronal loops, is shaped by magnetism. Without the magnetic field's influence, the sun would be a far more monotonous star. Instead, magnetism makes it a living, breathing, and sometimes tempestuous entity. Sunspots are the most visible signs of the sun's magnetic moods. They tend to appear in groups, often as pairs linked by a great looping magnetic field. One spot will have a north magnetic polarity, the other a south, like opposite poles of a bar magnet. The arc of magnetism connecting them traps cooler plasma in its grip, outlining structures we sometimes see as prominences, towering loops of glowing gas that stand above the sun's surface. Sunspots grow and shrink as the magnetic fields beneath them strengthen or decay. Over days or weeks, a complex sunspot group may evolve. An enormous energy builds up in its tangled magnetic knots. There is a rhythm to these appearances. Roughly every decade or so, the sun swings from a time of few sunspots to a time of many, and back again. At the peak of this cycle, dozens of spots can dance on the sun's face. At the low point, the sun's visage is often clear and quiet. Each cycle, the sun's magnetic poles even flip. North becomes south, and south becomes north, as part of this regular heartbeat of our star. Our sun, like a living thing, has its seasons of storm and calm. When the stress in twisted magnetic field lines becomes too great, they can suddenly snap into a new shape, much like a tensed rope that finally breaks free. In that instant, the energy that was bottled up in the field is explosively released. This is a solar flare. On the sun's surface, a flare is a blinding flash of brightness, a sudden blaze of radiation across the spectrum. It is as if a patch of the sun's surface has detonated with the power of countless nuclear bombs. In minutes, a flare unleashes a torrent of X-rays and charged particles into space. If the Earth lies in its path, these emissions race toward us at light speed, arriving just minutes after the flare erupts. Our planet's upper atmosphere suddenly swells with energy. Radio communications can crackle and fade as the ionosphere, the atmosphere's charged upper layer, is pummeled by the onslaught, and astronauts in orbit might hastily seek shelter from a burst of radiation that moments before was not even known to exist. Flares are often accompanied by an even more massive eruption, the coronal mass ejection, or CME. Where a flare is a flash of light and high-speed particles, a CME is a giant cloud of solar plasma hurled out from the sun. When a particularly complex magnetic loop in the corona destabilizes, it can fling away a chunk of the sun's outer atmosphere entirely. Imagine a colossal bubble of electrified gas, more massive than all of Earth's oceans combined, suddenly launched into space and expanding as it races outward. A coronal mass ejection can contain an astonishing amount of matter and energy, an immense, billowing stormfront in the emptiness of space. If one of these solar tsunamis is aimed toward Earth, we will know it soon enough. Within a day or two of the eruption, the wave of solar particles reaches our planet. Earth's magnetic field recoils and reverberates from the impact, like a bell struck by a hammer. We call this disturbance a geomagnetic storm. When a geomagnetic storm engulfs Earth, the results can be both beautiful and dangerous. Under the night skies at high latitudes, ghostly lights burst forth. Auroras, the northern and southern lights. Normally, auroras are confined to the polar regions, tracing the shape of Earth's magnetic field as it directs the sun's particles toward the poles. But during a strong solar storm, auroras can be seen much farther from their usual homes, painting the skies in eerie greens, purples, and reds over a vast swath of the world. Imagine waking in the tropics to find the night sky alive with rippling curtains of light. Such an astonishing sight has indeed occurred when the sun lets loose one of its great storms. In ages past, people who witnessed auroras far from the poles were often terrified. They saw in them dragons or celestial armies, believing the heavens were aflame with omens. To ancient peoples, these luminous dances in the sky must have been both wondrous and terrifying. Even today, knowing their true cause, one cannot watch the aurora's shimmering display without a feeling of reverence for the forces at play. Yet along with this beauty comes disruption. The same geomagnetic tempest that sets the skies aglow can wreak havoc on our modern technology. The barrage of charged particles and the distortion of Earth's magnetic field can induce surges of electric current in long conductors here on the ground. In our age of wires and wireless signals, a strong solar outburst can interfere with radio transmissions, scramble GPS navigation, damage satellite electronics, and even overload power grids, plunging cities into darkness. Over a century ago, a monumental solar storm made telegraph lines spark and catch fire. Telegraph operators found they could disconnect their batteries and still send messages. So powerful were the electrical currents coursing through the wires. If a storm of that magnitude struck today, satellites might be knocked offline, and extensive blackouts could occur. For all our technological might, we remain passengers in the sun's domain, subject to its occasional fits of violence. This turbulent interplay of solar magnetism and its effects on Earth and the planets is what we call space weather. Like weather in Earth's atmosphere, it has calm days and tempestuous days. The sun's magnetic field is ever shifting, and as it does, it breathes out gusts and squalls into the solar system. Most of the time, the solar wind blowing past Earth is a gentle breeze, and our planet's magnetic field shrugs it off with little fanfare. But when the sun erupts, the space around Earth becomes a stormy sea. A surge of charged particles and magnetic disturbances crashes against our planet's defenses, and near-Earth space itself reacts in kind. Auroras lighting up, satellites feeling the shock, currents coursing through the ground below, where all seems quiet. Fortunately, Earth has a sturdy shield. Our planet's magnetic field envelops us, carving out a protective bubble that the solar wind must flow around. This magnetosphere diverts most of the charged solar particles, allowing only a portion to funnel down toward the poles. In the clash of sun and Earth, the auroras are the glowing traces of our magnetic shield intercepting the solar storm, a testament to the protection it offers. Planets without a significant magnetic field, like Mars, have no such guard. Over eons, the sun's relentless particles stripped away much of Mars's atmosphere, leaving it a cold, arid world. In that fate, we see mirrored the dual nature of our sun, the gentle provider that sustained life on Earth, and the relentless force that can erode a planet's very sky. It nourished Earth with light and warmth, while its winds slowly wore Mars down. Magnetism is the hidden architect of the sun's behavior, from the steady cycle of sunspots to the wild drama of flares and auroras. Through it all, the sun continues to shine steadily in our sky, a reassuring beacon of day. But we have learned that beneath that steadiness is a flickering heart of magnetic energy. The sun's calm and its storms are two sides of the same coin, both born from the same stellar heartbeat. As humanity extends its reach into space and relies ever more on technology, studying and forecasting this space, weather becomes increasingly important. We now watch the sun with eyes open, tracing its spots and flares, listening for the whispers of its solar wind. We have even sent spacecraft to touch the sun's fringes, sampling its corona and feeling its magnetic embrace, all to better understand our star's moods. In the midst of these stellar tempests, it is easy to lose sight of the sun's most gentle and steadfast gift, the sunlight itself. Every day, countless photons leave the sun and stream across space, and some of those reach our world to illuminate the sky. Consider for a moment a single particle of light, a photon, born in the sun's core. It began as pure energy released by a fusion reaction in that dense, searing heart. For untold years, it fought its way through the sun's interior, scattering and dancing through the radiative maze, slowly migrating to the surface. At last, it broke free from the photosphere, joining the radiant tide of sunlight that floods out into the darkness. In that instant, it set out across the cosmic gulf at the ultimate speed, racing through the vacuum toward our small planet. After a brief voyage through the abyss of space, the photon pierces Earth's upper atmosphere. Perhaps it is dawn, and this tiny messenger of the day slips through a clear sky to reach a waiting leaf on a tree. The photon is absorbed, its energy triggering the chemistry of life, photosynthesis, helping a green leaf turn carbon dioxide and water into sugar. In that moment, a bit of the sun's energy, carried across the cold void by a single photon, becomes part of a living plant. Another photon falls upon a human face and is absorbed in the warm skin of someone standing under the morning sun. Nerves register the gentle heat. The mind welcomes the comfort. That warmth is a direct touch from our star, a tangible link between our flesh and the nuclear fires at the sun's heart. Every ray of daylight that we see, every soft beam reflected by the moon at night, began in the sun's core long ago. The sunshine that makes the petals of a flower glow, that draws a child's laughter on a bright afternoon, that dances on waves at dusk. All of it is energy forged in a star and sent outward as a gift across the emptiness. It is literally starlight. The light sustains the winds and rains of Earth's weather, drives the engines of life, and paints our world in color, each sunrise and sunset. From the sun's perspective, these photons are a way it reaches into the darkness, touching worlds with its essence. From our perspective, they are life and time itself. Every meal we eat is sunlight captured by plants. Every sight we behold is enabled by the sun's illumination. Thus, the sunlight we feel on our skin carries an ancient story. It is the end of a journey that began in the heart of a star and a bridge between our everyday lives and cosmic processes. In that golden glow, the tumult of the sun's interior and the fury of its storms are gentled into a nurturing radiance that gives life rather than takes it. We are, in every sense, bathing in the light of a star. To stand in the sunshine is to be touched by the cosmos, to be warmed by a process that has been ongoing for eons. The next time you see dust motes dancing in a sunbeam or feel the sun's warmth on your face, remember that you are feeling the afterglow of a journey that spanned the depths of space and countless years, a journey from the core of a star to the core of your being. Beyond the orbit of Earth, the sun's influence continues in a quieter but no less significant form. The solar wind that billows out from the corona fills the solar system with a tenuous, invisible presence. Space is not truly empty. It is filled with the sun's breath. This stream of charged particles flows outward past all the planets, carrying with it a stretched-out imprint of the sun's magnetic field. It's as if the sun, through its wind, reaches out to touch each world in its orbit, linking them in a web of invisible threads. As the solar wind encounters each planet, the effects depend on whether the planet is protected by its own magnetic field or left exposed. We've seen how Earth's magnetic bubble deflects the wind, diverting the charged particles around us. Jupiter and the other giant planets have formidable magnetic fields that carve out even larger sanctuaries in the solar wind. When the solar wind presses against these magnetic bubbles, it sparks auroras at their poles too. Jupiter's polar skies glow with curtains of light far more intense than Earth's, and even Saturn wears ethereal rings of auroral light. On worlds like Mercury, or our moon, which have little or no magnetic shielding, the solar wind slams directly into the surface. It can embed particles in the soil and slowly sputter away atoms into space. Mars, with only patchy magnetic fields and a thin atmosphere, has its skies occasionally set aglow by diffuse auroras, a reminder that even without a strong magnetosphere, the solar wind still makes its presence known. Perhaps the most visually stunning evidence of the solar wind's reach is found in comets. When a comet from the frigid outer reaches of the solar system ventures close to the Sun, it sprouts a luminous tail that always points away from the Sun. This is because the solar wind, along with the gentle pressure of sunlight, is pushing material off the comet's nucleus and sweeping it into a tail that streams far into space. Every comet's tail is essentially a windsock, revealing the direction of the Sun's breeze. In ancient times, people saw those mysterious comets with their glowing tails stretching across the sky, and perhaps sensed that the Sun and the comet were interacting. Now we know it is the breath of the Sun, gusting through space, that draws those ephemeral streaks. The solar wind is not a steady, featureless breeze. It has structure and gustiness. Fast streams of solar wind can overtake slower ones, creating turbulent regions out in the depths of space. Magnetic clouds and shock waves from solar eruptions course through the wind, eventually overtaking planets or other spacecraft that lie in their path. The wind also carries the Sun's magnetic polarity outward. At times, Earth finds itself connected to the Sun by magnetic field lines stretching across interplanetary space, allowing energetic particles from solar flares to spiral directly toward us. In this way, the solar wind is the medium that transmits the Sun's influence throughout its domain, like a great cosmic ocean in which the planets sail. As our solar system journeys around the center of the Milky Way, it carries this protective bubble along. The Sun, like a bee in a giant swarm, orbits the galactic core among billions of other stars. One lap around the galaxy takes an unimaginably long time. In the Sun's long life so far, it has only managed a few dozen such circuits. On this grand voyage, our star drifts through changing cosmic neighborhoods. Sometimes the space around it is relatively empty. At other times it might encounter wisps of nebulae or the lingering echoes of ancient supernovae. These encounters can subtly influence the boundary of our heliosphere, perhaps even nudge comets from the distant cloud at the fringes of our solar system. We ride along on this stellar odyssey, a family of planets wrapped in the Sun's embrace, cruising through the galaxy's spiral arms. It is a humbling thought that our entire existence, every life, every story told under the Sun, has been carried on this great galactic journey, and it will continue long after we are gone, the Sun forging ahead through the dark with its tiny companions in tow. Eventually, at some immense distance from the Sun, the solar wind begins to meet resistance. The sparse gas that drifts between the stars pushes back against the Sun's advancing wind. The solar wind slows, compresses, and finally, at a certain boundary, it can push no further. The continuous expansion of the Sun's atmosphere is halted by the presence of the wider galaxy. This boundary marks the outer edge of the Sun's influence, the frontier of our star's dominion. Here, the solar wind's long journey ends, merging into the interstellar medium. This invisible border defines a vast bubble around the Sun, known as the heliosphere, a cocoon of solar particles and magnetic fields that envelops all the planets. To step outside that bubble is to enter truly interstellar space. For decades, the solar wind was only a theory, an idea to explain why comet tails always point away from the Sun. It wasn't until humanity ventured into space with probes that we felt this wind firsthand. Our spacecraft have measured its particles and tasted its composition. Finally, after decades of journeying, a tiny spacecraft built by human hands passed through the boundary of the heliosphere and sailed into interstellar space, becoming the first emissary from Earth to enter the realm between the stars. It confirmed the existence of that distant frontier and carried with it a golden greeting from our world as it moved under the dim light of a sun now far behind. The sun's breath, it turns out, has a limit. Within that limit, within that bubble, the sun is Lord and life-giver. Every world we have ever known lies inside this protective sheath blown by our star. Now, standing at the edge of the heliosphere, we gaze outward and backward to the realm of the galaxy beyond, and backward toward the sun at the center of its bubble. We can appreciate the true scale of our star's influence. The sun is not just a disk in our sky. It commands a vast region of space, sculpting it with light and wind. It has forged a safe haven in the galactic sea, a place where its family of planets resides. To understand the sun fully, we must also understand how stars like it are born and how they die. For our sun is one among billions, each with its own story of origin and fate. Our journey now moves beyond our solar system, beyond the present moment of our sun's life, to the story of how such stars come into being and how they transform over time. Stars are born in darkness, far from the bright bustle of any galactic core, in the quiet spiral arms of galaxies like our Milky Way. Vast clouds of gas and dust drift in cold obscurity. These are the stellar nurseries, enormous nebulae stretching across light years of space, rich in hydrogen and sprinkled with heavier elements forged in ancient supernovae. Within these great clouds, gravity works patiently and silently. A slight densification, perhaps triggered by the shockwave of a distant exploding star or the brushing encounter of two clouds, begins to draw matter toward its center. As the gas compresses, it heats up and starts to glow faintly. What was once invisible in the darkness becomes a warm ember hidden inside a cocoon of dust. This is the birth of a star, or rather, the first whisper of a star yet to be. As the cloud fragment collapses under its own weight, it often breaks into smaller pieces, each destined to form a star, or even a small cluster of stars. In each fragment, matter spirals inward, and as it falls, it begins to spin faster, like a twirling ice skater pulling in her arms. A flattened disk of gas and dust forms around the growing central mass, whirling like a carousel. At the center of each collapsing fragment, a protostar, a baby star, is taking shape. It is not yet a true star, for it has not begun nuclear fusion, but it shines with the heat of its gravitational contraction. We can imagine it as a glowing orb buried deep within a dusty womb. If we could pull back the veil of dust and look inside, we would see a scene both serene and violent. The protostar's surface roiling with convection, jets of gas erupting from its poles and piercing out into space, and the surrounding disk feeding material steadily onto the growing stellar infant. In these concealed cradles, many stars are often born together, siblings in a stellar brood. Some are destined to be massive and brilliant, others small and faint. For a brief time, the protostar continues to gather mass. The infalling gas rains down mostly onto the disk, which then funnels onto the star. The star grows, and the pressure and temperature at its center climb ever higher. When the core temperature at last soars to the threshold, where hydrogen atoms begin to fuse into helium, a profound transformation occurs. The protostar becomes a star. It is as if a switch is flipped in its core. The darkness inside ignites into light. The star begins to generate its own energy by the same nuclear process that powers our sun, and a new sun bursts into existence in that once dark place. With that first ignition of fusion, a stellar wind, much like the solar wind of our sun, often springs from the newborn star, and intense light from the hot young star pours into the surrounding space. These forces blow away the remaining shreds of the natal cloud, dispersing the cocoon that once hid the star. If the star is massive enough, its fierce radiation may carve fantastic shapes in the parent nebula, creating glowing cavities and pillars of dust that resist the onslaught for a time. Before long, what was once an opaque dark cloud becomes a cluster of shining new stars. Its birth cloud eroded to wisps around them. The siblings now bask in each other's light as they drift together, loosely bound by gravity. Our own sun was likely born in such a cluster of stars. It may have had many siblings forming alongside it in a long-vanished nebula, all of them cocooned together and then emerging into the galaxy's light. In that stellar nursery, the sun's siblings would have shone nearby, sharing a common region of space for a time. But over the ages, the cluster dispersed. Each star, including our sun, went its own way, moving through different orbits around the Milky Way. Today, the sun's sisters and brothers are scattered, indistinguishable from the other stars of the galaxy, though astronomers scanning the sky have identified a few stars with chemical fingerprints so similar to the sun's that they might be long-lost solar siblings. In the collapse of a nebula and the birth of a star, we see nature's cycle of creation at work. The gas and dust that form new stars carry the ashes of previous generations, the carbon that will someday course through the veins of living creatures, the oxygen that will fill their lungs, the silicon that will form rocky worlds. All these atoms were fused in stars that lived and died before our sun was born, then mixed into the clouds from which new stars arise. Each generation of stars enriches the galaxy further, seeding the raw material for planets and life. Thus, when a new star like our sun ignites, it carries within it the legacy of cosmic ancestry. Around many newborn stars, the leftover gas and dust in the disk coalesce into smaller clumps, giving birth to planets, moons, comets, and asteroids, the makings of a new solar system accompanying the new sun. From afar, a stellar nursery like the Orion Nebula offers us a glimpse of this wondrous process. Through telescopes, we see stellar embryos still swaddled in dust, others breaking free and burning blue-white with youthful energy. We see great columns of dark gas, cosmic pillars, being eroded by the radiation of hot young stars hidden within them. In that radiant chaos, worlds are being formed, and light that will shine for billions of years is first kindled. Starbirth is at once delicate and cataclysmic. Delicate in the slow, inexorable gathering of a star's first light, and cataclysmic in the way a newborn star's brilliance can rip apart the very cloud that gave it life. From these nurseries emerge all stars, whether destined to be mighty blue giants or dim red dwarfs. The process is the same, guided by the pull of gravity and the laws of physics that govern heat, pressure, and fusion. We have journeyed from our sun's neighborhood out into the broader galaxy to witness the origin of stars. Now, having seen how stars take their first breath, we can explore the grand tapestry of stellar variety, the many kinds of stars that fill the cosmos, from the smallest embers to the most luminous beacons. The stars that populate the universe are as diverse as the creatures in a great ocean. They come in different sizes, colors, and brightnesses, each type with its own character. Astronomers classify stars by their temperature and luminosity, which often correlates with color. Just as iron glowing in a blacksmith's forge changes from dull red to orange to white hot as it gets hotter, a star's color tells us its heat. The coolest stars are deep red, smoldering with a subdued cherry glow. Hotter stars shine in yellow and white hues. The very hottest stars blaze with blue-white brilliance, their surfaces incredibly hot. The smallest true stars in the cosmos are the red dwarfs. These diminutive stars contain only a small fraction of the sun's mass and glow feebly, often with a light so faint that none are visible to the naked eye from Earth, despite being the most numerous stars in the galaxy. A red dwarf is usually much smaller and cooler than our sun, giving off a ruddy light. But what they lack in brightness, they make up in longevity and ubiquity. The vast majority of stars in the Milky Way are thought to be red dwarfs, quietly burning their fuel at a glacial pace. A red dwarf may live for an almost eternal span of time before it runs out of fuel. In these diminutive furnaces, the flame of nuclear fusion is weak but extraordinarily steady. Some of the smallest red dwarfs can continue to shine for longer than the current age of the universe. On the other end of the stellar spectrum are the blue giants and supergiants. These stars are born with many times the mass of the Sun. They are extremely hot and brilliant, shining with a fierce blue-white light that can be seen across great distances. A blue giant star pours out an enormous amount of energy, consuming its hydrogen fuel at a prodigious rate. Because of this, its life is intense and fleeting. It will exhaust its core fuel in a cosmic eye blink, a mere moment compared to the tranquil longevity of a star like our Sun. Some of these massive stars do not stay blue-white for their whole lives. As they age, they swell and cool, turning into red supergiants that can be truly colossal in size, their bloated atmospheres expanding outward to stupendous dimensions. Imagine a star so large that, were it placed where our Sun is, it would extend beyond the orbit of Earth and well into the realm of Mars. These red supergiants glow with a cooler, reddish light, but they are tremendously luminous due to their sheer size. They are rare and splendid beacons in galaxies, heralds of impending cosmic change, for they live fast and die spectacularly. Between these extremes lies a rich variety of stars. There are orange dwarfs, slightly smaller and cooler than the Sun. There are white stars, somewhat hotter and more massive than the Sun. And there are stars like our own, yellow-white and medium-sized, often called main sequence stars or dwarf stars by astronomers. Our Sun, in fact, is considered a dwarf star in this sense, not because it is especially small, it is larger and more massive than most stars, but because it is in the prime of its life, steadily fusing hydrogen in its core. It hasn't yet bloomed into a giant. In terms of mass and brightness, the Sun is fairly average, but because the faint red dwarfs are so inconspicuous to our eyes, most of the individual stars that dazzle us in the night sky are actually more luminous than our Sun. Many of the bright stars we see at night are larger, hotter, or more energetic than the Sun, which is why they stand out from afar. Meanwhile, countless dim red stars nearer to us go unnoticed without a telescope. Stellar classification also includes exotic categories. There are the supergiants we mentioned, both blue and red, which are essentially stars on steroids, far larger and more luminous than ordinary stars. And there are stars at the very brink of not being stars at all, the brown dwarfs, sometimes nicknamed failed stars. These objects form in the manner of stars but do not accumulate enough mass to ignite sustained hydrogen fusion in their cores. A brown dwarf glows faintly with leftover heat from its formation, and perhaps with brief flashes of fusion of heavier forms of hydrogen, but it gradually cools and fades, acting more like a giant planet than a true star. Brown dwarfs fill the gap between the largest planets and the smallest red dwarfs, and they add to the menagerie of objects in the galaxy. Nature produces stars in a continuum of masses and sizes, from tiny red embers that burn for practically eternity to stellar titans that blaze with incredible intensity and then perish in the blink of an eye. Each type of star has its own destiny. A star's mass, set at birth, is the key that unlocks the rest of its life story. With a high mass comes a glorious but short-lived existence as a giant, likely ending in a dramatic explosion. With a low mass comes a long, steady burn and a quiet retirement. Having surveyed the variety of stars, the small, the medium, the great, we can now follow one typical star, perhaps not unlike our Sun, through the stages of its life, from its youthful radiance to its final farewell. Let us trace the fate of a star much like our Sun, now that it has burned in the heavens for eons. For a long time, such a star shines steadily, fusing hydrogen into helium in its core and bathing any nearby worlds in stable light. But the fuel at its center is finite. Eventually, after many billions of years of shining, the hydrogen in the core dwindles. The balance that sustained the star for so long begins to tip. With less fusion to support it, the core of the star starts to contract under its own gravity. As it contracts, it heats up, much as a bicycle pump grows warm when you compress the air inside. This extra heat flows into the shell of hydrogen that surrounds the inert core, a shell that still has hydrogen left to burn. And then something dramatic happens. Hydrogen in this outer shell, now at extreme temperatures thanks to the contracting core beneath, ignites in fusion. The sudden onset of shell burning causes the star's outer layers to push outward. The star swells enormously in size, turning into what we call a red giant. Its surface cools as it expands, shifting from yellow-white to orange-red. But the star's interior becomes hotter than ever, and its luminosity soars due to its sheer size. Our once modest sun-like star becomes a bloated colossus. In this red giant phase, the star's radius can grow far larger than it was in its youth. If our sun were to undergo this transformation, it would likely engulf Mercury and Venus, and perhaps even Earth, turning those worlds into charred cinders swallowed by the expanding stellar fire. The sky of any surviving outer planets would be dominated by the star's enormous disk, a brilliant coppery orb covering a huge swath of the heavens. Deep inside the red giant, the core continues to shrink and heat, as it is now made mostly of helium ash, the byproduct of those long ages of hydrogen fusion. When the core grows hot enough, a new kind of fusion begins. Helium atoms start fusing together to form carbon and some oxygen. Our star, which was facing death, finds a second wind. The onset of helium fusion in the core, often beginning in a sudden burst for a sun-like star, something astronomers poetically call the helium flash, stabilizes the star for a time. The core expands a little and cools, and the star's bloated outer layers contract somewhat from their extreme size. The star settles into a new equilibrium, a helium-burning giant. In this phase, the star's color might become a bit more yellowish as it slightly shrinks, and its surface temperature rises again, and it burns steadily once more, though its remaining lifetime is now comparatively brief. But helium, too, is a finite fuel. In time, the core's helium is exhausted, leaving an inert mass of carbon and oxygen, the carbon and oxygen that were created by the helium fusion. For a star like our Sun, no further fusion is possible in the core. The temperatures required to ignite carbon are beyond its reach. With fusion ceasing again in the center, the core of the star, now a dense ball of carbon and oxygen, contracts yet further. Meanwhile, helium fusion may continue in a shell around the core, with hydrogen fusion still going in a shell above that for a while. This causes the star to swell once more, even larger than before. The giant star becomes highly unstable in this final stretch of its life. It pulsates, growing and shrinking, trying to find balance, but never quite succeeding. Each expansion and contraction shakes loose some of the star's outer layers. Gentle at first, these pulsations turn into violent throes that throw vast clouds of the star's outer atmosphere into space. The star is literally coughing away its own substance, shedding its mass like tears into the void. Eventually, the entire outer envelope of the star is cast off, blown away into space as a gorgeous gossamer shell of gas. For a brief time, that expanding shell is illuminated by the hot, exposed core at the center, and it shines as a glowing, multicolored cloud known as a planetary nebula. To an observer afar, it is a sight of eerie beauty. A round or ring-shaped mist, glowing where once there was a star, often with intricate patterns like delicate rings or hourglass forms. This is the dying breath of a star like the Sun. a final gesture of beauty as its outer layers, now free in space, fluoresce in the stellar twilight. What remains of the star itself is the central core, now revealed, a ball of carbon and oxygen about the size of Earth, tremendously hot but no longer sustained by fusion. This is a white dwarf, the ember of a star's heart. It glows white-blue with residual heat, initially extremely hot, though its small size means its total light output is relatively modest. A white dwarf is one of the strangest forms of matter in the universe. It is supported not by heat or ongoing fusion, but by the quantum pressure of electrons, a fundamental resistance of matter to further compression. Its density defies imagination, the mass of a sun compressed into a sphere the size of a planet. A spoonful of white dwarf material would outweigh a mountain. In this exotic, degenerate state, the stellar core will sit and slowly cool for time spans beyond human comprehension, fading from white to yellow to red, and eventually toward blackness. Thus ends the life of a sun-like star, not with a bang, but with a serene farewell glow. The mighty red giant's cast-off shroud becomes part of the galaxy, seeding space once more with elements like carbon and oxygen that will one day find their way into new nebulae, new stars, new planets, and perhaps new living beings. The white dwarf that remains is like a stellar tombstone, an extremely dense crystal of carbon and oxygen. Some have likened a white dwarf to a cosmic diamond, marking where a shining sun once lived. Over eons, it will cool further and dim, eventually becoming a black dwarf, a hypothetical cold dark sphere, the final quiet cinder of a once radiant star. The universe, however, is not yet old enough for any white dwarfs to have cooled completely to black. That final stage lies in the far future, far beyond the present age of the cosmos. Our sun will one day follow this very path. It is the destiny of all stars in its weight class. But not all stars share the same fate. The most massive stars, those bright blue giants we discussed, live dramatically different lives and meet far more violent ends. Before we return to the personal tale of our own sun's future, let us first briefly touch on the spectacular final act of those heavier suns, a fate that leaves behind some of the most enigmatic objects in the cosmos. While a star like the Sun ends its life in relative peace, the same cannot be said for the giants. The most massive stars go out with staggering violence. After burning through hydrogen and helium in a cosmic rush, a high-mass star, far more massive than our Sun, doesn't stop at carbon and oxygen. Its core, under tremendous gravity, continues fusing heavier and heavier elements in layers, like the layers of an onion. Carbon fuses into neon, neon into oxygen, oxygen into silicon, each stage burning faster and yielding less energy than the last. Finally, the core is transmuted into iron, the ash of nuclear fusion, an element that cannot release energy by fusing further. When enough iron accumulates in the core, the star faces an irreversible crisis. With no new energy to support it, the iron core collapses in on itself in a fraction of a second. The core implodes, and densities reach such extremes that atoms are crushed. Protons and electrons melt into neutrons. The core, which was once perhaps the size of Earth or smaller, shrinks to a sphere only a few miles across in an instant. In that moment of collapse, a phenomenal amount of gravitational energy is released. The infalling outer layers of the star hit this super-dense core and rebound outward in a titanic explosion, a supernova. The star's death throes are so violent that for a brief time, the exploding star can outshine all the billions of other stars in its galaxy combined. The supernova blasts the star's outer layers into space at incredible speeds, and shockwaves race through the expanding debris. Temperatures in the explosion briefly soar so high that elements heavier than iron are forged in the fiery crucible. Gold, silver, uranium, and many others are synthesized in those final furious seconds. These newly minted atoms are hurled into the cosmos to mingle with the gas and dust that will eventually form new stars and planets. What remains at the center of this cataclysm is the collapsed core. If the star was only moderately massive, on the lower end of the massive star range, the core's collapse is halted by the pressure of densely packed neutrons. Matter squeezed so tightly that the neutrons resist any further compression. The core becomes a neutron star, an object of incredible density and exotic nature. A neutron star packs more mass than our Sun into a sphere only a few tens of miles wide. It is essentially a giant atomic nucleus, a ball of neutrons left behind by the supernova. A thimbleful of neutron star material would outweigh a mountain. Neutron stars often spin rapidly. The parent star's rotation speeds up dramatically as it collapses, like a pirouetting skater pulling in her arms, and they may possess intense magnetic fields. Some neutron stars sweep beams of radiation from their magnetic poles as they spin, like lighthouses in the cosmos. These are observed as pulsars, blinking radio or X-ray beacons, marking the location of a neutron star across the galaxy. For the most massive of massive stars, even neutron degeneracy pressure cannot hold the core up. If the collapsed core is above a certain critical mass, nothing known can stop its collapse. It continues to shrink until it essentially vanishes from view, forming a black hole. In that case, the stellar remnant has crushed itself into a point of virtually infinite density, enveloped by a region of space from which nothing can escape. Not even light can climb out of the warped space around the collapsed core, hence the name black hole. What was once the heart of a star becomes a kind of cosmic abyss, a pit in the fabric of the universe. A black hole can be thought of as the star's ultimate tombstone, carrying its mass hidden within a distortion of space-time. We infer its presence only by ghostly tracers, the desperate whirl of gas and dust spiraling into invisibility, flaring in X-rays as it vanishes, or the subtle quivering of space-time itself when the black hole is jarred by the fall of something massive. When a supernova finally fades, it leaves behind these strange remnants, a neutron star or a black hole, and an expanding cloud of gas and dust that was once the star's outer layers. In time, that cloud will cool and disperse into the interstellar medium. The elements cast into space will blend with other matter and eventually become part of new stars, new planets, and perhaps new life. Massive stars, though few in number compared to red dwarfs, are the great alchemists and fireworks of the universe. In dying, they sow the heavy elements across the galaxy, the very elements that make rocky planets and organic beings possible. Every atom of calcium in your bones, of iron in your blood, was forged in the belly of a star that ended in such a blaze. The cosmic ashes of supernovae fertilize the galaxies, ensuring that each new generation of stars is born with a richer array of ingredients for planets and for life. We have traced the lives of stars from gentle birth in nebulae to either a quiet sunset as a white dwarf or a cataclysmic finale as a neutron star or black hole. But our exploration of suns would be incomplete without considering that stars rarely live in isolation. Most have companions or families of their own, multiple star systems bound in gravitational dances, or retinues of planets that circle around them. Our sun itself has a family, the planets, including Earth, and smaller bodies that formed from the disk of dust left over from the sun's birth. And many stars form in pairs or trios, locked in orbits around each other. To truly understand the nature of suns, we must also look at these relationships, the celestial communities that stars form, and the diverse planetary systems that have arisen around distant suns. Each star in the night sky is a sun in its own right, and many are far from solitary. In fact, most stars are born as multiples, two or more suns bound together by gravity, orbiting a common center. Imagine a binary star system, two suns locked in an elegant dance, circling each other over years or centuries. From a distance, they might appear as a single point of light, but up close, each partner star swings through space in response to the other's pull. Some binaries are widely separated, each star carrying its own retinue of planets. Others whirl so close that they can trade gas, or even, in extreme cases, merge into one. In a triple or quadruple system, the dance grows even more complex, with stars tracing intricate paths around their mutual center of mass. The universe is a grand stage, with every stellar configuration you can imagine. There are suns that eclipse one another from our viewpoint, causing their combined light to rhythmically dim and brighten, cosmic beacons signaling their orbital waltz. There are stars so close that they share a common envelope of gas, two stellar hearts wrapped in one glowing shroud. And there are systems where small companion stars orbit giant ones in distant loops, like tiny sparks flitting around a great flame. Around many of these suns, planets coalesce and circle, for planet-making is a natural companion to star-making. When a star is born from a spinning disk of dust and gas, the leftover material often forms worlds. Our own solar system is one example, a handful of major planets and a retinue of smaller bodies. And we have learned that planets are astonishingly common. We now know that planets accompany stars throughout the galaxy. Astronomers have discovered innumerable exoplanets orbiting distant suns, and they suspect that for every star we see, there are likely worlds in attendance. There are planets that cling close to their stars, scorched and locked by gravity, so that one hemisphere endures endless day while the other is in perpetual night. There are planets at just the right distances from their suns, the so-called habitable zones, where conditions might allow liquid water and the chemistry of life. Some planets orbit twin suns, experiencing double sunrises and double sunsets, their skies graced by two stellar disks. Imagine standing on such a world, with two faint shadows dancing on the ground, or on a world under a dim red dwarf sun, where the daylight is a brooding ember, and the stars' frequent flares paint the sky with sudden ruddy hues. Each planetary system is a story of creation, just as every star's life is a story. Some stars have giant guardian planets that shield inner worlds from comet bombardments, as Jupiter helps shield Earth. Others have planets in wild, elongated orbits, leading to chaotic swings of climate. Some massive stars might not host long-lived planets at all, as their fierce radiation and short lives can blast away or outlast any nascent worlds. But around the more common, steady stars, the red dwarfs, the orange dwarfs, the sun-like stars, there are surely many planets that have persisted for eons, perhaps even giving rise to life. Under alien suns, if life has blossomed, creatures might gaze up and see a sky tinted by a different color of star and wonder about the warmth that gives them life, just as we ponder our sun. For us, those other suns have been points of curiosity and imagination for as long as we've had eyes to see the stars. Only recently have we begun to detect some of their planets directly, to see the telltale dip in a star's light as an orbiting world passes in front of it, or to measure the slight wobble of a star tugged by the gravity of unseen companions. Each discovery is a revelation, proof that our sun and its family are not unique, that the cosmos is filled with solar systems. It humbles us, yet also makes the universe feel more intimate, a place where countless stars shine down on their own worlds, as the sun does on ours. Now, after journeying so far through stellar nurseries, fiery demises, and distant solar systems, we return our focus to our own star, the sun, and reflect on its ultimate destiny, and on what it means for us to live beside a star. And so we return to our sun, the star that has accompanied every moment of humanity's existence and that sustains all life on Earth. The sun today is a middle-aged star, steadily burning its fuel and kindly bathing our world in light. It has shone in our skies for longer than any living thing can remember, and will continue to shine for ages to come. But the sun, too, is mortal in the cosmic sense. Nothing in the universe lasts forever, not even a star. In the far future, long after our species and all we know may have turned to dust, the sun will begin to change. When its core can no longer sustain the fusion of hydrogen, it will respond by growing in size and luminosity. Our sun, so familiar and constant, will swell into a red giant. Its light will turn the color of copper and blood, and it will loom colossal in the sky. The innermost planets will be engulfed in its fire. Mercury and Venus will surely be devoured. Earth may meet the same fate, or be left a charred and barren rock, its oceans boiled away, its surface desolate and scorched. For any life remaining then, these changes will be catastrophic beyond measure. But likely, by that distant era, Earth will already be quiet and lifeless, or life, if intelligent and capable, will have found refuge elsewhere. The sun, once a gentle guardian, will become an inexorable destroyer of the very life it once nurtured. Yet even in this fierce transformation, there is a strange grandeur. As the sun's red giant phase reaches its climax, it will cast off its outer layers. Our star will shed its shining mantle, which will expand outward, drifting into space. For a short time, those cast-off layers will form a beautiful planetary nebula around the dying sun, a glowing testament to its passing glory. Future astronomers, perhaps from other surviving worlds or civilizations yet unimagined, might look toward our solar system and see a delicate shell of gas, like a cosmic flower blossoming and fading, shining in remembrance of the star that was. At the center of that nebula will remain the sun's core, now exposed and shrunken to a white dwarf. This final stage of our sun's life will be a small, hot sphere no larger than Earth, composed mostly of carbon and oxygen. The sun's very heart, left glowing like a lonely ember in the night. It will shine white and then blue-white, slowly cooling over the course of billions of years. The brilliance of the day that once was will recede into a gentle twilight. The white dwarf sun will illuminate the ghostly nebula for some thousands of years, but eventually it too will fade, perhaps becoming a black dwarf in the far, far future. The solar system will drift in darkness and silence. This is the ultimate fate of our sun, to swell in glory and then to divest itself of its brilliance, leaving behind a small, dense core that will quietly glow and then dim to darkness. It is a fate that the sun will meet far in the future, an inconceivable gulf of time beyond our lives. In knowing this, we find both melancholy and solace. Melancholy that all things we know are transient, that even the great sun will one day wither and leave the sky empty. Solace that we and our world have yet long epochs in which to live under the sun's light, and that when the end comes, it will be part of the natural order of the cosmos, the same finale that countless sun-like stars have already played out in the quiet reaches of the galaxy. And perhaps, too, there is a kind of triumph in this ending. The sun's final nebula will return its substance to space, enriching the interstellar clouds with elements that once made up Earth and us, and every living thing that sunlight ever touched. In that way, the sun's death will seed new beginnings elsewhere. Some of the carbon and oxygen from the sun's core might drift for ages and eventually become part of new stars, new planets, new life. As it has always been in the universe, one star's end is another's beginning in the endless cycle of creation. Now, stepping back from this entire journey, from the birth of stars in dark nebulae to the blaze of supernovae, from the quiet glow of the sun's youth to its fiery demise, we find ourselves contemplating what it means to be the children of a star. To live beside a star is to live in a state of grace between wonder and knowledge. We orbit a massive, luminous being that gives us everything: light, warmth, the very possibility of life. and yet asks nothing in return. Our ancestors felt the sun's power and worshipped it. They built legends and monuments to honor it. We, with all our modern understanding, have not lost that reverence. How could we? Each dawn when sunlight spills over the horizon, painting the sky in rose and gold, we feel the same awe that ancient watchers felt as the morning star ascended. In that daily miracle, night yields to day, cold yields to warmth, and the world is renewed. We know the science of it. The earth is turning, bringing us once more into the sun's light. But knowing takes nothing away from the magic of feeling it. Beneath the facts and figures, there is a simple truth. The sun is the source of our being. Every meal we eat is sustained by sunlight captured by plants. Every warm breeze that caresses our skin, every drop of rain that falls, is driven by the sun's heat, nurturing our planet. And our bodies themselves are made of material created in long-dead stars and powered by the sun's current light. We truly are made of stardust, shaped into conscious form and given the spark of life by a star's energy. In a very literal sense, we are children of the stars. When we say we are born of starlight, it is not just poetry, it is lineage. The elements in our flesh were brewed in stellar furnaces, and the energy that ignites our living cells is a gift from our sun. Our story and the sun's story are inseparable. Think of the connection. A baby born on a bright morning, crying out with lungs filled for the first time. Those lungs draw in oxygen that a star, billions of years ago, forged in its core and then cast into space. The baby's parents smile in the sunlight that streams through the window, sunlight that left the sun just moments earlier, having traveled across empty space to fall upon that new face. A chain of events spanning eons and light years has culminated in that ordinary, extraordinary moment. Starlight becomes life. The cycle continues. Standing here on Earth, we look up and see a blue sky by day. But beyond that blue lies the black tapestry of space and the brilliant stars. Our sun is one among many, and though we cannot see those others by day, they are there, distant and shining. At night, when our sun has set, we glimpse the wider cosmos of which our star is a part. We see the Milky Way's misty band, made of uncountable suns, and we realize that our little home orbits just one humble star on the edge of a vast galaxy. The humility of this perspective is profound, yet it does not diminish us. It elevates us. We are part of something immense and beautiful. The stars that speckle the night sky are our cousins. Some may have planets with beings who look up at their own sun and feel the same wonder. In the end, the story of suns is the story of creation itself. It is an ancient tale, told in the language of light and gravity. It began before we were here and will continue long after we are gone. But for a brief moment, we get to be conscious participants in this grand drama. We get to study the sun, protect ourselves from its tantrums, bask in its warmth, and dream under its light. Our lives, like mayflies, flicker in the daylight of this star. But while we are here, we behold the splendor of the cosmos through the window that our sun's light provides. As we conclude this journey, imagine once more the sun hanging low at dusk. The sky blazes with color and the shadows grow long. In that sunset is a reflection of the entire epic. Day turning to night as stars appear one by one, the cycle of light and dark that has guided life's rhythm from the beginning. The sun will rise again tomorrow, as it always does, bringing a new day. But even when it eventually rises no more, the legacy of its light will live on in everything it touched. We live on the brink of a star's fiery grace, taking our nourishment from its hand and daring to learn its secrets. We are small, but we are also a way for the universe to know itself. Matter that was once scattered across space, now gathered and alive, pondering the star that gave it life. In the dance of sunlight and shadow, we find meaning, comfort, and inspiration. Our sun connects us to the universe and to each other, a common star, binding all living things in a shared radiance. So when you next stand in daylight, feel that warmth and remember, you are heir to an ancient covenant between Earth and Sun. Every photon that touches you carries a message from that central fire, that life is precious and intertwined with the cosmos. Our world exists because a star shines. And in the atomic hearts of stars, in the silent roaring of their nuclear fires, in the gentle glow that crosses the void, the universe has found a way to nurture consciousness and wonder. This knowledge, this feeling, is humbling and uplifting all at once. The Saga of Suns is indeed a cosmic poem, forged in light, breath, and gravity. It is written across the heavens in the glow of nebulae and the ashes of supernovae, in the rising of each morning sun and the eternal glitter of the night. It is a poem we are part of, every one of us made of star stuff and sustained by starlight. In knowing this, we find not despair at our smallness, but gratitude and awe that we have the privilege to dance in the light of a star, and through that light, to glimpse the eternal.